This last lecture, we will discuss a diffused interface version of the problems we have discussed so far. And this is actually the original motivation for all this work that for me starts in 2016. And the question was how you can construct a approximation of Plateau singularities using the one-phase Allen-Kahn model. Because this is something that very explicitly you can't do. So there is a theorem that tells you that you can do that. At the same time, the Allen-Kahn energy is a physically correct model for liquids at equilibrium as much as Gauss capillarity. So there is a bit this, I would say, mystery, right? So how is that a physically correct model cannot describe a physical singularity, right? So what's wrong? So assuming that you're not necessarily familiar with the Allen-Kahn model, let me remind you about the basics of the Allen-Kahn theory. So, so one way of looking at Allen-Kahn is as to a diffused interface approach to capillarity theory. So in capillarity theory, we had the container omega and the liquid droplet E at equilibrium inside the container. So the variable was a set. In Allen-Kahn, the variable becomes a density, so a function with values in 0, 1. And then the idea is that where your function is equal to 0 or is close to 0, you have the air phase. Where this function is close to 1, you have the liquid phase. And then where your function takes all the values in between 0 and 1, you have the actual transition from liquid to air. And this transition, there is a length parameter in the Allen-Kahn model. So it's not one model, it's a family of model, okay, parameterized by this parameter epsilon. And epsilon is a length. So why, first of all, you want to do that, right? So why do you want to say, rather than using the position of the droplet, I decide to use a function with values in 0, 1, okay? So, and this really comes from statistical mechanics and the idea of um, um, defining models, introducing mathematical models that try to approximate, to understand, for example, a liquid or with a description that is intermediate between the atomistic or molecular level and the continuum level. So U physically represents the probability of observing a molecule of liquid or a molecule of air at a given point, or the relative fraction in a abstract unit of space of the two, okay? With the idea that this is really, even at equilibrium, is really a sort of system with dynamics, right? That there is an exchange, there is molecular chaos, there is temperature, and so there are molecules of liquid and molecules of water, and there is evaporation, and there is so on and so forth. So this is a bit the idea. Now, Allen-Kahn, from that viewpoint, is not the kind of model that you derive in statistical mechanics for a liquid at equilibrium. Okay, so the actual models that you derive are a bit more mathematical, from the point of view of the mathematical properties, are worse than Allen-Kahn. So Allen-Kahn is a sort of regularization of those models. So it's a bit better. The energy that you use, so this is somehow the variables you want to use. So a function with values in 0, 1. And now the model you want to use for a function with variables in 0, 1 to look like the position of a droplet with constant mean curvature. So the energy that you use is the Allen-Kahn energy of, I call it step epsilon, but it's not really step, I mean, it's the length scale of the interface that you want to observe. So the energy take the following form. You have a Dirichlet energy with this parameter epsilon in front, and then the parameter epsilon becomes 1 over epsilon, so it's a very large constant times W of u. So this is so this W I've tried to write it W in blue consistently because W in red is the wireframe for us, right? So, but the Allen-Cahn the double well potential, it's again a W, so you have two Ws. Now when you write in LaTeX, one it's a bold W and the other one is a standard W. Here it's just red and blue. So it's very deep considerations. So this is the function u with values in 0, 1. The double well potential, here there are various school of thoughts. Okay, so there is people that the function u is defined on R or on 0 infinity, and the double well potential is defined on R. So you can do whatever you want. At the end of the day, the meaning of this thing is that u is a probability or is a density, and so for me it takes values in 0, 1. So, but the problem is that my double well potential doesn't look like a W anymore because I just have the, okay, so it's called a double well potential because it goes like this, of course, right? But I mean, just, okay, again, very deep considerations here. So, and I work with something that is the simplest possible double well potential. So double well potential will, as is 0 only at 0 and at 1, otherwise it's positive. The derivatives are 0 and the second derivatives are positive. Okay, so Allen-Cahn has been around for forever, and all the things that I'm going to talk about, you can do them for potentials with different kind of behaviors near the double wells. You can change the Dirichlet energy with all sorts of functions. So it's a immense literature. This is somehow the simplest possible Allen-Cahn model you can write down. So I was mentioning statistical mechanics. So in statistical mechanics, yes, yeah, yeah, yeah. I don't know, and it's called the Canilliard, and it's called the what? I mean, so, uh, I don't know. I mean, it's yeah. Yeah, I don't know if it's a correct terminology, to be very honest. I mean, definitely so a lot of so I think that the story of this model is this that it's so statistical mechanics, you don't have the gradient of u square here. You have so you have a double integral and you have ux minus uy, and here you have something like j of x minus y, and this j is compactly supported and smooth, which is kind of horrible because it means that the finiteness of this interaction energy doesn't imply anything. So you don't have a regularity theory. So it's like the Euler-Lagrange equation is just that a certain convolution is equal to some semilinear term. So it's really horrible. So then, for example, you can do this thing, for example, with fractional energies. When you do the fractional case, right, this thing becomes 1 over n plus 2s, then it's a singular interaction kernel, and then you have a regularity theory, also non-local. So, so this thing is a sort of, the fractional case is a sort of thing in between Allen-Cahn, which is nice because there's a change, and the thing that comes from statistical mechanics. Mm, so that and the model that comes from statistical mechanics, if one wants to look at it in the literature, this is called, I think, the Gates, Penrose, Lebowitz functional. So the problem of statistical mechanics is that there is uh, a- an incredibly vast literature about technologically and scientifically super important problems that are mathematically very difficult, extremely difficult, right? So there is a lot out there in terms of insight that doesn't translate into mathematical theorems. And then there is people discovering and rediscovering and coming back at it again and again. And each time they overlap, and that's why it's so delicate to to now the thing is recording, so I can't say really more, but uh, when we stop the recording, I can talk more about statistical mechanics. I mean, there is some very recent events, yeah, that are really instructive, related to, of course, of the solution of the Hilbert 6 problem. So it's it's really a so here, I mean, yeah. So for example, now I'm going to present. Actually, I can explain this in a moment. So there's definitely, for example, a paper of Gertin from the 80s or the 70s, where he presents some conjectures, right, about the behavior of these things, and then the actual proofs of these theorems come with the gamma convergence setting. So how do you actually prove these theorems? And then again, it depends how much people cares about proofs and so on and so forth. Not everybody cares. So I care. So Allen-Kahn is an approximation of capillarity. Uh, let's say that we are in a bounded container. So Allen-Kahn with a volume constraint. So we fix the integral of u to be equal to our volume parameter v. As epsilon goes to 0, we converge to the capillarity problem. Meaning that if you consider a family of minimizers u epsilon of the Allen-Kahn energy with fixed volume, then up to subsequences in epsilon going to 0, there exists a minimizer of the capillarity energy so that the u epsilon converge in L1 to the characteristic function of this minimizer, and the Allen-Kahn energy goes to the capillarity energy. Okay? So this is a first indication that you're doing the right thing. Moreover, this is even more interesting, you can look at the Euler-Lagrange equation solved by this minimizer. So we know that the capillarity model is solved with constant mean curvature and the Young law. The Allen-Kahn model is going to be, so this function u epsilon, you can really imagine as in my first slide that is approximating this characteristic function. The level set of the function, so the boundary of E is intersecting the boundary of omega at 90 degrees. And then this condition on the normal derivative tells you that the level set of u, epsilon, meet the boundary of the container at 90 degrees. So this is a reflection of the Young law. But now it's diffused because it holds all along the boundary of omega, not just at the contact, okay? And then there is the Euler-Lagrange equation. This is just the Euler-Lagrange equation of Dirichlet energy, and you get your Laplacian, and oh, I misplaced the epsilons. Oh my gosh, this is horrible. Okay, this is kind of alarming. So this is a 2 epsilon Laplacian of u and 1 over epsilon w prime, of course. I don't know why I inverted the epsilons here. Okay, let me write the correct equation on the blackboard because this is confusing. So yeah, so I'm sorry. So it's 2 epsilon Laplacian of u epsilon equal to w prime of u epsilon over epsilon minus lambda epsilon. But luckily I didn't forget to write in blue the w, so the important things are there. And with the convergence of the Lagrange multipliers. Okay, so this really tells you that these, okay, so this already tells you why you care about these, for example, from a numerical viewpoint. Because convincing a computer about finding a surface with constant mean curvature inside the domain, it's, I don't know. Here you're solving a semilinear elliptic PDE, okay? There is, of course, the small epsilon in front of the Laplacian, which makes it, okay, which makes it more difficult, but it's still a semilinear PDE. So somehow you are doing an approximation of this geometric variational problem that it's easier to compute. So this is definitely an important feature. And even from, but it's not just the computational side of the story that it's important. There's also the technical side. For example, you know that there is a theory for constructing critical points to equations, right? These equations, they come as Euler-Lagrange equation of some energy. So one way of solving this equation is minimizing. So you do global minimization, you find the global minimizer. But there are plenty of situations and definitely minimal surfaces where you don't only have global minimizers, you also have local minimizers, you even have critical points that are local maxima, right? So how do you prove that an equation has more than one, an Euler-Lagrange equation has more than one solution? And the classical technique is this min-max method. Okay, so you try to, if you have two minima, you consider all the paths, and then you swipe with this path, and then you find the maximum point by this saddle point method. Okay, so this is something that for elliptic PDEs, semilinear elliptic PDEs, is very well understood. Okay, the Ambrosetti-Rabinowitz theorem is one piece of relatively basic mathematics. Okay, it's a kind of functional analysis that gives you that kind of meta theorem, so you know how to find them. So there is a very robust scheme to find critical points and counting them and finding their index and so on and so forth. So it's an all theory extremely well developed. When you try to do these in geometric variational problems is way more difficult um, because you don't have a good regularity theory for critical points, first of all. So there is this work by Pitts, who was a student of Almgren, who I think in the late 70s or in the 80s created a min-max theory for the area function. The problem of that min-max theory is that because of the lack of regularity, it's extremely difficult to apply it and getting an object that you actually want to look at. Okay, you will get some wicked varifold that with some weak regularity theory. So, and it's definitely, even when it's successful, the approach, it's extremely complicated to use. Okay, so one thing that was realized recently is that you can avoid all of that by, in a sense, doing your min-max methods on the Alencane energy, okay, and then taking a limit of that constructions. That's much easier and gives you effectively the same kind of results than rather trying to do the whole min-max method without leaving the geometric setting. So you do the min-max method at the epsilon level, and then you pass to the limit. So this is just to say, I don't know if this explanation was clear because it kind of calls for a lot of context that maybe is not familiar to everybody. But this is just to say that this is a useful approximation of the area functional under many viewpoints, theoretical, computational, and so on and so forth. So, and also scientifically, because it comes from kind of simplifying the models of statistical mechanics, okay? So it's really one of the basic models of for droplets. Yes. Yeah, of course. Yeah, it's just so you can do. So here I am approximating a capillarity theory with the relative adhesion coefficient equal to 0, but you can approximate the capillarity theory with a relative adhesion coefficient between -1 and 1. There is a paper of Modica on Archive for Rational Mechanics sometime in the 80s again, where he does all the details of that too. I think, if I remember correctly, it's Modica. For sure, he did the one with alpha equal to 0. Yes. Yes, so this is the normal boundary condition here comes from the zero contact angle. They are just parallel, right? And then you have to change it if you're approximating the hydrophilic or hydrophobic capillarity, you will get a different conditioning, okay? Yeah, because it's still a contact angle, yes. Yeah, you have to change, exactly, yeah. That's the natural thing, the only thing it can be, because then when you take the limit, you have to converge, right? So it's not that you have much choice. So, and okay, this operator with the right epsilons, I will fix them, I'm sorry for that. This is the diffuse mean curvature operator, okay? So really this quantity is, this will be a function over the whole domain, and this function will not have a geometric meaning at a lot of points, but near the interface, okay, this is the mean curvature of your diffuse interface. So the diffuse interface will be a layer, an epsilon layer around the boundary of the limit surface. And in that region, this density is approximating the mean curvature. So you can do, okay, I think it's not, okay. There is a bit of lag between the screen, but now it seems updated. Okay. So you can do the things, this approximation both ways. So I proved that a sequence of minimizers is going to converge to a minimizer of capillarity, but you can also go the other way around. So you can say, let me start in a domain omega with a minimal surface and assume that your minimal surface comes as the boundary of an open set, E. Okay? Then, which essentially it's always the case locally, uh, of course, then there are, of course, like minimal surfaces that are Moebius strip-like minimal surfaces that are not boundaries, okay? But somehow, generically speaking, you will see these, right? So you will be able to write your minimal surface as a boundary. And then you can always construct sequences of families of functions U epsilon that converge in L1 as epsilon goes to 0 to your characteristic function. The Allen-Kahn energy converges. And these solve again, the epsilons are wrong here, the Allen-Kahn equation with the normal boundary condition. Okay? And the key point here is the smoothness, because how is this thing constructed, right? I will explain in a moment. But so somehow the smoothness of the limit function here is crucial. So you're doing a construction. Let me explain this. So, so if you want to approximate this interface, omega intersection boundary of E, essentially you give yourself a layer of size epsilon, right? And you want to go from 1 to 0 in an epsilon of space. So the way you achieve that is you look at this. I really have to show you another computation. I will explain in a moment how this is done, okay? Um, I'll come back to that. So, but before I come back to that, let me show you an even more, much more difficult result, more recent too, by Tonegawa and Vikramasekera. So in this result, they consider what we could call diffused stable minimal surfaces. So they have a bunch of solutions, now the epsilons are correct. They have a bunch of solutions to zero diffuse mean curvature in omega, right? That's the equation up there, that are stable. So here I've written what stability means for the Allen-Kahn equation. It means that the second variation is non-negative. Of course, the second variation of the Dirichlet energy, it's still the Dirichlet energy. There is a 2 in front because you took derivatives. And then there is this W second, which is, of course, the second derivative of the... So you have this quadratic form in phi, and that quadratic form in phi is non-negative. Of course, W second is not positive, okay? W second will be positive near the wells, and then it's negative. So that's why this inequality is non-trivial. It's not automatic. Okay, so if you have a family of diffused stable minimal surfaces with bounded energy, let's assume that the dimension is less than, ambient dimension less or equal than 7. Then their theorem is that there exists a smooth minimal surface such that subsequentially as epsilon goes to 0, U epsilon converge to S in the weakest possible sense. So you look at the energy density of these U epsilon, and now I've called them Uj because I am on a subsequence epsilon J, okay? This is the quantity that I take the integral of to compute Allen-Kahn. So I look at it as a random measure. So that's the integrand of the Allen-Kahn energy times the Lebesgue measure. So this energy density will be 0 most of the time, right? Because away from the transition region, the gradient is at 0, W of 0 is at 0. So, or inside the droplet region, again, U is constant, close to be constant 1, W of 1 is 0. So this measure is going to be concentrated in the transition layer. Um, and it's concentrated in a small space, takes large values, and then this converges as a radon measure to the integration over this minimal surface. However, if you want, the tragedy of this theorem from the viewpoint of Plateau laws is that the limit S is smooth. That's it. So I was mentioning Almgren pits, diffuse Almgren pits, right? Min-max methods. So this is a key theorem to do that, because it tells you that these critical points that you have constructed at the epsilon level will converge to a smooth minimal surface, which, when you want to use these things to prove the Wilmer conjecture, is yay, because, okay, you got a smooth surface and you can do your tricks on it. So that's actually the good feature of this theorem. From the point of view where I am coming from, of understanding Plateau singularities, this is puzzling, right? Because I have told you that this Allen-Kahn has its whole pedigree as a model for droplets, comes from statistical mechanics. It's okay, it's a bit of an approximation, but still the features are there. So where did we lost Plateau singularities, right? Because those things are real. So, and this is a bit this slide here, right? So Allen-Kahn converge to the area. Plateau singularities can be derived by area minimization. The Allen-Kahn approximation of the area converges only to smooth minimal surfaces. That's essentially what we have learned, okay? Because Vikramasekar and Tonegava tells us that this is going to be the case. So, with these very naive questions, okay, in 2016 I was at ICTP, which is a Center for Theoretical Physics, and I asked the physicist there, Antonello Scardicchio. You may remember the name because it was involved in one paper I mentioned in the second lecture, and was involved in formulating these models. So when I asked Antonello, okay, but what is wrong? Because is Allen-Kahn maybe not always the correct model to understand the phase transition? And immediately said, absolutely not. That's physically, it's a correct model. I mean, there is no way that this is wrong. But you had to add the volume. This was like a 5 minutes conversation. So for a physicist, the immediate answer is that you can't see them with Allen-Kahn because you're not adding the volume, of course. And then, okay. Okay. And then I say, okay, let me add the volume. But first, let me do it with the capillarity theory, because adding the volume while doing Allen-Kahn, it seemed, having two layers of difficulty. So, and then it's yeah, you have a question? Yes. So, yeah. So, what Reynaldo is talking about is this other option. So, Allen-Kahn, so if you remember in the very first slide, I mentioned that I want to study one phase Allen-Kahn. So one phase Allen-Kahn means that you have a liquid in a surrounding medium, okay? So it's really two phases, it's the liquid and the air, okay? Then there are models that are called multi-phase Allen-Kahn models, where your variable, rather than being a scalar function, so my variable is a scalar function, right? But you can have a model where your variable is a vector function, and each of these functions is responsible for describing the phase of one substance, okay? So, and then you have a variant of the thing. So you have a sum of epsilon Dirichlet energies of each of these guys, and then you have a double well potential that tells you that you really like to see only one of them at a time. So my double well potential tells me it's super convenient to do only air, and it's super convenient to do only liquid because they cost zero, and you pay some to transition between the two. And now you can cook up a double well potential with multiple wells, okay, which is happy when only one of them is one and all the others are zero. So if you do that, say with n equal 3, so you have 3 phases, okay, you can construct you construct an Allen-Kahn model that will see something like here u1 is equal to 1, here u2 is equal to 0, sorry, is equal to 1, here u3 is equal to 1, okay? And where 1 is close to 1, the others are close to 0. You can construct that. And you will do a sort of vector valued Allen-Kahn approximation of the tripole point. This is, for me, this is not what happens in a soap film. Because in a soap film, it's not that I have water, oil, and air. Okay? In a soap film, I have water around the Y point. So the point is what the physical model matter. I mean, unless what you're trying to do is just having a mathematical model that computes something, this is okay, then it's fine. Or if you're modeling multiple fluids that are immiscible and then they cannot mix, and so okay, that's a physically motivated model, okay? But the question here is, can you do this with one phase Allen-Kahn? And the reason why this is a question for me, at least, is that the one phase Allen-Kahn perfectly approximates the area under so many viewpoints, right? Area minimization is compatible with Plateau laws. This approximation is incompatible with Plateau laws. So where is this thing breaking down? Does it make sense now? Okay. And the answer is at the volume, apparently, which I don't know what it means. If not that, well, I know I couldn't understand why these. Honestly, I don't understand even now why for a physicist it's so immediate to say that. But that's what came out as a response. So what I did, and I'm mentioning this not because I'm trying to write my biography here, but I mean, I think that, again, it's part of a school, right? I mean, if the students survive, right, and you keep doing mathematics, you have to find your own problems. So I think it's also good to know at times, I mean, where these problems come from, right? I mean, how people go by and develop a series of papers, right? So in this case, I started with the Gauss capillarity theory. So now you know from the previous three lectures that the Gauss capillarity theory with the volume, we have done it. Okay, it works. And we'll learn quite a few things about it. So at a certain point in the past years, I felt ready to go back to the diffuse problem, which was the original question. So, okay, but then what happened when there was also Allen-Kahn, right? So, um, so this is the model. I mean, that's the first attempt at the model. So we have our usual wireframe closed set, omega the complement. Now we have two parameters, the volume and the epsilon of Allen-Kahn. We minimize the Allen-Kahn energy among W12 functions with a volume constraint and with the condition that the function u is C-spanning the wireframe, which is, of course, something that needs to be defined and will be a bit the heart of the matter, because what does it mean that this function is spanning W, right? I mean, it's clearly a delicate point. So, but before we talk about how we do the spanning, there is another point. On a bounded set, on a bounded container, we have already said that minimizing Allen-Kahn at fixed volume converges to the capillarity theory model, right? However, when omega is unbounded, if you minimize Allen-Kahn just with the L1 volume constraint, you see nothing because there is a problem with scaling. And in the Plateau problem, omega is unbounded because it's the complement of the wireframe, right? So we cannot, I mean, this model with the fixing the integral of u is not going to work. It's going to be a trivial variational problem. So your function u will just splatter down with very large support, and this will be energetically convenient. So let me explain why. And let me explain what is the volume constraint we are going to impose. Okay. So this is the really usually the first computation you see about Allen-Kahn or the Modica-Mortola functional. This is the Modica-Mortola trick indeed, right? Universally known as the Modica-Mortola trick. So you have your Allen-Kahn density energy here, and then you do this arithmetic geometric mean inequality with the modulus of the gradient and the square root of W of U. Okay? And now the quantity that you have, the lower bound that you have here, so if you call phi the primitive of the square root of the double well potential, right? And you look at phi composed with U, the gradient of phi composed with U will be square root of WU times gradient of U. So will be its absolute value will be what you have here. So this computation tells you that the Dirichlet energy, the Allen-Carr energy density is bounded from below in an epsilon independent way, which is the crucial point, by the absolute value of the modulus of the gradient of this composition of U with this function phi. So why is that important? Because you see, the problem in analyzing this energy as epsilon goes to 0 is that the bound on the derivative is degenerate, of course, right? So you are not going to get any compactness from that directly. However, this simple argument tells you that on a family of functions U epsilon with bounded Allen-Carr energies, even if you don't have a W1 to bound, you still have a bound in W11 on phi composed with U. Actually, a bound in BV. Okay, so phi composed with U will converge indeed not to a W11 function, but to the characteristic function of a set of finite perimeter. So what are the properties of this function phi of U? So phi of U is going to be the integral between 0, it's going to be the primitive of square root of W. So we are going to do the normalization where the integral between 0 and 1 of the square root of W is equal to 1, so that phi of U converges to the characteristic function of V, not to 5 times that or whatever this integral is. And the important point is how phi, the important point for the point I want to make is how phi behaves near 0. Remember that W prime is 0, W second is positive, so W of t is t squared near 0. So square root of W near 0 is t, I do the integral, it's t squared again. So phi behaves quadratically near 0, okay? Now, since I control the total variation of phi of U, by the Sobolev embedding, Allen-Carr controls the total variation of phi of U. The total variation of phi of U controls the ln plus 1 over n norm of phi of U. Okay? Yes. Yes, if you have exactly. So whenever you have a uniform up and bound in epsilon, right, you're going to control this quantity. Notice here I'm integrating over Rn plus 1 because I'm applying the isoperimetric inequality, and here I put the constant of the isoperimetric inequality to 1 because I forgot. And and now the important point for the volume constraint, you see that phi composed with U to the n plus 1 over n, it's really U to this power slightly larger than 2. 2 to the power n plus 1 over n. So that's the power of U that, in a sense, is compatible with the rescaling properties of this energy, not the integral of U. So that's, if you want, the explanation of why you can make the energy small enough by keeping the volume constraint. So that's a spreading of U is going to keep you can do that while keeping the volume constant, equal to your parameter V, and then you're just losing the energy because both the Dirichlet and the W are going to 0 if you're very almost constant everywhere. But this is the kind of thing you cannot kill by spreading by the scaling variance of this BV Sobolev inequality. Okay, so of course I'm not going to work with a power because it's just we're directly going to with phi of U. So phi of U phi of U to the power n plus 1 over n is going to be our volume potential. Okay, so this is the model. So we are going to say that we minimize Allen-Carr among Sobolev functions for which the integral of V of U is constant equal to small v, where V of t is the potential defined by this complicated formula. Okay, it's the primitive of square root of w raised to the power n plus 1 over n. Okay, you may protest. This is not elegant. This is not beautiful. This is not simple. But the answer is we don't really care because the approximation, the Allen-Kahn model is not W, okay, is not computed out of the molecular properties of anything, okay? So W is a convenience here for us. So the model is, as they say, phenomenological. You observe something and you construct a model that computes that something, that models that phenomena that you're seeing, okay? So here, essentially, we are happy, as far as V of U goes, as far as the potential that we use to fix the volume, we are happy with whatever choice of V, okay, is going to give us that in the limit as epsilon goes to 0, the limit set as volume E. Then we are happy. Okay, we don't really care about the specific form of V. What is important is that it is a form that works. Actually, this particular V is not even that nice because near 0, it behaves with this super quadratic power that from the point of view of the semilinear PDEs that we're going to work with is going to be a bit of an annoyance, okay? Because it would have been much better to have a square there, for example, or a 1 for sure. So the fact that we are in this unbounded domain forces us to get something slightly different. And then this even introduces some technical difficulties. But at the end of the day, it's a volume potential and the volume constraint is taken care of and we are happy with it. So, and this V also 0 in 0, 1 in 1 because of our normalizations, okay? Now we have the volume constraint. And sorry, I promised you to talk about these two. Then I will start moving a bit faster. So you see when we did the modica mortola trick, right? As epsilon goes to 0, this inequality sign becomes closer and closer to inequality. Okay? And no, but I don't have time to explain this. So let me move on. Sorry. If I have time at the end, I will. Okay. Yes. Mm-hmm. Mm-hmm. What, sorry? Yes. So the problem is that if you work with the integral of u, no, from the PDE side is a bad choice because it's making it harder, right? But the point is that the infimum, the minimization problem, is going to be ill-posed if you work with the integral of u. Because you're on an unbounded domain and the integral of essentially any power of u less than 2n plus 1 over n, I can construct a sequence of functions in that minimization problem that will bring the energy to 0 while keeping the volume constraint, simply by splattering around the mass everywhere, the volume everywhere, okay? So, and these, in a sense, it's a choice that doesn't have that problem because, okay, because you have to prove that it doesn't have that problem, but the indication that this choice will work is because it's the natural choice coming from the Sobolev BV embedding. Sorry, from the BV embedding, okay, on Rm plus 1. So this whole argument doesn't prove that the problem is well posed. But this argument tells you that, well, it tells you that this problem, the inf is not 0 for sure, because you have this lower bound in terms of v to the n plus 1 over n. Okay, so it gives you indication that that problem may be solved. Then, of course, you have to work with this thing and prove that everything goes well. But if the question is why this choice is, clearly I need to make another choice. I cannot work with the integral of u by counterexamples. And now I propose to use this. Okay, and then I was commenting that even if this choice maybe doesn't seem elegant, okay, at the end of the day, we don't really care. We don't really have a strong choice to have a particular volume potential. At the end of the day, it's just the only thing that matters is when you send epsilon to 0, this volume constraint on U translates into the right volume constraint on E. So the volume of E equal to V, it's a physical, geometrically meaningful thing when I say volume of E equal to V. When I say integral of some potential of U equal to V, you know, it's more free, the choice of the potential that I use. Yes. Mhm.
the change of variable. Just you can just say that V of U is the physical object because
Yeah, and then you have a different functional. You don't compute the Dirichlet energy of that, right?
they, that, so it's only different.
Yeah, but the energy here you have to do the Dirichlet energy of what? Of V minus the inverse of V of, I mean, I don't know. I don't think it's a particularly deep point. It's a point you have to make because otherwise the variational problem is ill-posed. And once you make it, you have to explain it because otherwise you're going to ask me why we have to work with this potential. And even if I make it, you don't like it. And it's understandable because it's a ugly potential. But at the end of the day, I think we need it. Oh, you like it? Okay. Okay, if you like it, then we're good. Okay. Yeah, but I mean, it's, yeah. So let's talk about the spanning. So U is C spanning W. What could it mean? So remember that when U is close to be the characteristic function of a set E, and now we have two theories, one where omega intersection boundary V is spanning, and another theory when omega intersection closure of E is spanning, right? So the basic idea that in the end will be what you do is to ask that U equal 1 is C spanning. The level set U equal 1 is the object that is doing the spanning. However, there is a huge problem with that. That this energy is defined on Sobolev functions. So U equal 1 is defined Lebesgue almost everywhere. Okay. We can do a bit better because they are Sobolev functions, okay? You can do so that U equal 1 is defined Hn almost everywhere if we are in a Rham plus 1. Still incompatible with the Harrison-Pugh homotopic spanning condition that require the set to be closed. So this was a super strong motivation to go to war with the Harrison-Pugh spanning condition. However, we tried to avoid the war. So what we did initially, we said, okay, let's not minimize on W12. Let's minimize on W12 intersection with C0. So we consider continuous Sobolev functions. So that if you formulate this problem on continuous Sobolev functions, you are definitely allowed to require that U equal 1 is C-spanning. Absolutely makes sense. What is the difficulty of that, however, is proving an existence theorem because you have to, even if the minimization class is W12 intersection C0, the compactness is just W12. So you get a limit. This limit is a W12 function. In which sense is the limit C-spanning now? How do you close the proof? What does it mean that you have found the limit that it's still doing the spanning? It is less desperate than it sounds because, as you have seen with the proof of Harrison and Pugh, you can do the regularity while you do the existence, right? So it's not that you are doomed to say my minimizer is W12 and that's it. You can try to do the regularity. However, doing the regularity for this, you will see what is the Euler-Lagrange equation of this problem later on in the talk, okay? It's a very delicate free boundary problem. So we weren't able to do the regularity while at the same time we were doing the existence. So we gave up on the idea of doing W12 intersection C0. And we said, okay, how do we get a spanning condition that allows us to work with sets that are only defined Hn almost everywhere? And this is why we ended up doing the measure theoretic overhaul of the homotopic spanning condition. Then once we did that, we realized that we could prove the existence theorem without doing competitors, without doing anything fancy, just by compactness, okay? And then and so on. And so it's like we could went back to what we had already learned and do it much better because we had this stronger tool. Okay. This said, U equal 1 is spanning would be good now that we have the measure theoretic homotopic spanning, up to taking in place of U, say U star, the precise representative. What we ended up doing, however, is not even U equal 1. Let me go directly to what we used. We use U star, so the precise representative, greater or equal than T, because super level sets are more robust objects than level sets. And then you ask that all the super level sets are spanning for all T's larger than 1/2 and less than 1. So it doesn't really care that you start from 1/2. You could have started from 1/3, from 2/3, right? Because they are monotonic. So the larger the T, the smaller the set. So, and if I am C-spanning, everything bigger than me is C-spanning. So this is really like saying U star greater or equal than T is C-spanning no matter how T is close to 1. Okay? This is the way we are going to formulate the problem. And the reason is that it's the kind of formulation that we can use to make the proofs work. Then once we have relaxed this concept of U spanning W that much, so we had to relax it a lot. We had to allow for stuff that is only defined Hn almost everywhere. We had to not define it in terms of U equal 1, but in terms of super level sets. So once we've done enough space, okay, we are able to prove closure theorems and compactness theorems in this class and do the existence, okay? So that's what will mean. It will mean that the precise representative greater or equal than T is C-spanning for all T between 1/2 and 1. And then at the very end, we will prove that, but it actually meant on the minimizer will have this much more reasonable property, okay? So this is the problem. Yes. So the regularity will come later. So now is really what it's written here. Okay, so you have Sobolev functions with this natural but not so good looking potential for the volume, and the U star greater or equal than T are C-spanning. And you may ask, why didn't you just say U star equal 1? Or the answer is because technically we couldn't close the proof directly working with U star equal 1. Okay, so we come up with this thing that a posteriori is going to be on a minimizer equivalent to, the minimizer is going to be continuous and is going to be equivalent to U equal 1. So it's going to be the thing that you would have liked, but somehow I want to make the point again, since it's a school, that you can get what you want, but definitely you have to make space for it before you can. So in this case, we can prove that there exist minimizers. However, we can prove that there exist minimizers only in the geometric regime where epsilon is a length scale. So epsilon needs to be sufficiently small with respect to the volume at the power 1/n+1. Now, this is not surprising because the Allen-Kahn energy, for example, the Allen-Kahn equation, it's this semilinear PDE, right? But it has a geometric meaning only when epsilon is small. And generally speaking, semilinear PDEs, Laplacian of U equal to f of U, are, it doesn't seem much, okay? Because there is only an f of U. What could happen? The answer is everything can happen. So it's like every semilinear PDE is a universe, okay? You can have so many different behaviors of solutions and so on and so forth. So they're really a rich structure, semilinear PDEs. Only a single semilinear PDE is a rich structure. So I have no idea what happens to this semilinear PDE when epsilon is not small with respect to the volume to the power 1/n+1. I don't even know exactly what this semilinear PDE means. Sorry. Okay, so it's really like so there exists a minimizer if epsilon is sufficiently small with respect to the volume, and so which is our geometric intuition. We have a droplet of volume V. The layer where the transition happens is an order of magnitude, many probably smaller than the rescale volume. Then, if we send epsilon to 0, while we keep the volume fixed or while we send the volumes, Vj's, to a positive volume limit, and we consider corresponding minimizers in these problems, then the energy Vj epsilon j converges to the psi bulk, the capillarity energy with bulk spanning of volume V0, and there exists a generalized minimizer such that the Allen-Kahn energy density of Uj goes to the energy density of the soap film capillarity model with bulk spanning condition. So the solution of this thing at positive volume converge to one of these wet things. So this is already a geometric limit, right? Because from functions to these structures with mixed 2D, 3D dimensionality, right? So this is the bit of a complicated formula with the multiplicity, but that's the familiar energy density that we had for the soap film capillarity model. You can even go, we already know that the soap film capillarity model with bulk spanning, if I send with 0 to 0, this is going to Plateau, right? But I can even do that in one step. So if I send the volume to 0, and at the same time, I send epsilon to 0 faster than v to the 1 over n plus 1, so the droplets, the wet part is becoming small, and of course the epsilon has to become much smaller than v to the 1 over n plus 1. But if you do both things at the same time, and you follow a sequence of minimizers of psi vj epsilon j's, then the energy is converging to twice the Harrison-Pugh energy. Here I'm missing a factor 2. And there exists a minimizer in Harrison and Pugh such that the Allen-Kahn energy density, and this W should be blue, goes to twice Hn of S. Okay? So you can even construct these solutions, and then by sending both epsilon and the volume to 0 in a certain order, relative magnitude, you can get the Plateau singularity. All right? Yes. Uh-huh. Mm-hmm. Yeah, these are all gamma convergence results. These are all gamma convergence results. They're not stated like that in the papers, but they're all so it's all like for a generic sequence, you prove the lower semi-continuity inequality, and then the approximations at times. I don't think we discussed the approximations, the gamma link sup inequalities, but I mean they're not particularly, yeah. So at the end of the day, yes, these are all also gamma. You can see them as gamma convergence results for sure. Yeah. Now, gamma convergence, I don't know. You have to be always careful, right? What is the declare the topology and stuff like that. So these I am less certain of, so in the sense that I didn't check formally anything. But again, I think that yeah, I mean it's yeah, exactly. So I think that so. But I mean, if you're not familiar with gamma convergence, so gamma convergence is the theory that you should get yourself familiar with to have the correct mindset to look at this kind of questions. I have done that as a kid, okay? So, and then, of course, it's not that you need then to say gamma convergence every time you do it, okay? You can also just do it. Okay. So this is this hierarchy of Plateau problems, right, that you get. So at the highest level, there is this diffused model with homotopic spanning, with its volume constraint, its weird spanning law. The minimizers will look something like that. So in particular here, this picture really sucks, but u equal 1 will really be a sort of actually u equal 1 will be a tripole point. And then the function will, so u equal 1 will be a Steiner tripole point. The function will be globally Lipschitz, and we will have matching normal derivatives across u equal 1. And then as you get closer to the wet part, these normal derivatives become flatter and flatter. So in the wet region, the gradient of u epsilon is really small. It's like you're very close to one. Kind of opens up to wet the thing, okay? That's the intuition. So this goes, epsilon goes to 0 to the subfield capillarity model with its collapsing and so on. We know that this goes to Harrison and Pugh, and we can even go from here to there if you want in one limit, but you have to, of course, fix the thing. So how is that this is not in contradiction with Vikramasakara and Tonegawa, right? Because you cannot cheat, right? So what happened? It happened that you added the Lagrange multiplier, of course. So this would be the Euler-Lagrange equation of this problem if everything was nice. So it's mean curvature operator, that is here. So variation of Allen-Kahn equal to constant times variation of volume. So the mean curvature operator, the diffuse mean curvature, is really this minus that divided by V prime. Because the mean curvature is the derivative of the perimeter, is the derivative of the area divided by the derivative of the volume. So now the point is that volume means nothing in a diffuse model, right? If the volume means integral of u, then the V prime is 1, and so you don't see it, okay? So in this Allen-Kahn model, the diffused mean curvature operator is this minus that divided by V prime of u epsilon. That's what is constant. So this is not the Allen-Kahn equation we started from, right? It's a different one because of the volume constraint. Okay, that's what walks around the Tonegawa-Vikramasakara theorem. We are not solving the same equation, otherwise there would be a contradiction, of course. It's a different equation. Okay. There is this transmission condition. So the equation holds only where u epsilon is strictly less than 1. Where u epsilon is equal to 1, you have the transmission condition. So here you use an orientation assuming that u epsilon equal 1 is smooth, which you have no idea about. So far it's just a W12 function doing this suspending, okay? You have you can define a normal to it locally, and then using this normal, you have two-sided normal derivatives, and they have to match. So you have this kind of tent profile, okay? Which is going to do this transition in this epsilon layer, and then the closer you get in the region, the wet region, when you are in the wet region, it starts opening up and it goes almost flat for the wet triangle with the volume and the spanning. Now, there is a super interesting question. So we can prove that this equation holds in distributional sense. So these will be integral identities, nasty integral identities, okay? Because it's not that you don't have the regularity for example, I want to explain how you formulate the distributionally because it's not as elegant as writing that. But that's where you want to go. So recently, Michael Novak and Daniel Restrepo, together with Anna Skorogobatova, who is a PhD student with Camillo Dell'Ellis in Princeton, was until when? Okay, 1 year. I'm wrong by 1 year. Okay, come on. ATTH, okay. So Michael, Daniel, and Anna prove this. So prove that the minimizers of our problem are locally Lipschitz continuous in omega. So locally means that they didn't prove the Lipschitz regularity up to the wireframe, uniformly up to the wireframe. But this in particular means that minimizers are continuous. So u epsilon equal 1 is suspending, okay? So at the end of the day, right, it works. So you get the right object. But, and also, okay, u is, say, with the regularity I've given to the potential is going to be, the potential I assumed in this paper is C11W. So u will be C3 alpha, where u is less than 1. So in particular, u is where the PDE holds u is decent, okay, as decent as W prime and V prime allow it to be. And finally, u epsilon equal 1 is going to be an n-dimensional smooth manifold. That's why you can make sense of this transition condition on a closed set of Hausdorff dimension less than n minus 1. Okay, so in R3, you will have this transition along a two-dimensional surface where you have this transmission condition, sorry, along a line, okay? And there may be singular points. So, okay, that's a lot, huh? I guess. Yes. Sure. Mhm.
One is non-interior, the line,
Yes.
so you were saying that
So it maybe let's try to draw.
style,
Yes. Yes. So if this is the wet object, right? So it's like saying that. So now this green is almost white. So I don't know if. So this will be u epsilon equal 1. And on this region here, on the wet part, u epsilon, yeah, it's less than 1, but it's close to 1. So here, and as epsilon goes to 0, if you just send epsilon to 0 and keep v fixed, it will open up. It's clear, but you would like to see it, right? Yeah.
about
No, but
very, very,
yes. That's how I understand it, at least. So, and then it must be that, so here, in these regions, you will have, with these, so something like this. So say that this is 0, 1. So in this region here, with this angle condition, it will go down very fast, right? And then as you start going in this region, here we still have a sharp transition, and here the gradient will be slower. So that's the difficulty of this problem at this point. You want to construct this guy. So yes, right. Yeah. This is strange. So my next problem, indeed, is constructing solution of this Euler-Lagrange equation. So this is something that there is a substantial literature on these problems, right? So for example, how do you construct a solution of the Allen-Kahn equation that converges to a Simon's cone? These are papers of Del Pino, Vey, um, Kowalczyk, and Musso, and I don't know, there is a whole team of people working on these things. Packard, Frank Packard, has several papers of this sort, Mazzeo. So all these situations where you have some geometric object and you try to understand how to construct solution. And the way you do this is you start from an ansatz. So you start from something that is not the solution of the PDE, but should be reasonably close to the solution of the PDE. So you need these insights to get a good starting point. And then you write the equation against your ansatz, and you try to find the equation for something that it's a modification of your ansatz that will give you an exact solution. And then you construct an iteration scheme to make the error smaller and smaller and smaller, and getting a better and better and better ansatz, and showing that your ansatz converges to something. So why would this be super interesting here, in my opinion? Because we have proved that such an object exists. However, what is the diffuse thickness around the collapsed part, right? And so all these questions, I mean, I don't see how you answer them unless you go and construct it, more or less. Okay? So I think this would be a nice problem. Although it's something that is really not in my technical area of expertise, how to do these constructions. Okay, so I really wouldn't know very well how to start. But I mean, it's clearly something that it goes in that area of PDEs results. Okay. Just in the last 2-3 minutes, I can tell you about something that just the statements. So these are few results that are upcoming. So a first result is this regularity theorem for, and now here it's completely invisible. So here there is a line of y point that goes to the boundary of the wireframe, but from the resolution of the picture to the resolution of the beamer is gone. Singularity has disappeared, which is normal because it's time, right? Kind of a regularization effect. So, so the essentially, so by using all these theory of partitions and these various tools that we have developed in the last paper, we realized that something you can do, actually, as much as we do this story of the lambda minimality of the components, and so we can use that circle of ideas in R3 for the Harrison-Pugh problem. If if the wireframe is the closure of an open set with C2 boundary, and you have a minimizer and you pick a point where the minimizer touches the wireframe, then in a neighborhood, the minimizer is either diffeomorphic to a half plane or to a Y cone that intersects orthogonally with the wireframe. So this actually, I mean, with the right ideas, is not a long proof, okay? It's not a complex result. It's more like, we realized we could combine all the tools available. I think this is interesting for two reasons. So first of all, if the wireframe is a curve, right, and this looks more like, let me prescribe a boundary curve, the result is completely open. We don't know what are the cones. Even when I get that kind of W, we don't even characterize, it's not that we characterize all the Angren minimal cones that go with these, okay? So this really results for the Harrison-Pugh minimizers. So we use minimality in a very heavy way. It's not even Algren minimality is enough for this argument that we have, okay? So, but I think it's still interesting because it's the Harrison-Pugh problem, and it's the Harrison-Pugh problem in the physical situation where the wireframe is a solid object, I mean, so still interesting. Then we have been able to prove both the Hausdorff convergence and the wetting conjecture. So for W closed, the spending class, you have a sequence of minimizers of the bulk problems with volumes going to 0. As we know from the previous lectures, you converge to twice Hn of a Harrison-Pugh minimizer. And you can prove the Hausdorff convergence. This is actually is coming not from a very different set of ideas that are already behind these theorems. It was really more like being willing of suffer a bit more, but it's already there. What is really new, requires a new idea, is how you get, in addition of this Hausdorff convergence, which again is not entirely trivial, as I explained the other time, because it's not that you have bounded mean curvature, density, area density estimates, and then it follows immediately from the radon measure convergence. And you don't have it actually, you know that the mean curvature is exploding, so you cannot have them, right? So, but we also have finally the wetting conjecture. So if the singular set is non-empty and you are below the dimensions where you have the Simon's cone, then you can prove that the Lagrange multipliers are going to minus infinity, as they should, and that the wet sets, EJ, Hausdorff converge to the singular set of the Plateau minimizer in the Harrison-Pugh problem. So how is this done? And this is my last slide. So, but just to give you an idea of the kind of tools that, it's again an idea from regularity theory at the end of the day. So in regularity theory, you have this family of important theorems that are called epsilon regularity theorems, okay? So this is an epsilon regularity theorem at very negative mean curvature. And for this object with our mixed dimensional objects, right? So my object will be some wet three-dimensional region, some two-dimensional stuff, and then again some wet dimensional region. But the kind of statement can be understood even if you've never seen an epsilon regularity theorem. So the idea is the following. Let's say that the statement is like in certain dimension n, lambda positive minus lambda will be the mean curvature, so that's a bit of strange notation. You have k a minimizer of the problem. So assume that there exists an epsilon. I forgot to write there exists an epsilon. Okay, there always exists an epsilon. So given n and lambda, there exists an epsilon depending on n and lambda, okay? Which is the epsilon appearing in these estimates, okay? So if you are below, if you are sufficiently carved, then you have the following sort of cleaning property. What is the cleaning property? So let us assume that K union E, so the dry and the wet part, are trapped inside of a cylinder of height 1. They're actually trapped in the same cylinder of horizontal radius 1, but in an epsilon layer. So you know that, okay, there may be wet part, dry part, but all happens in a very tiny layer. How tiny depends on the bound on n and lambda, okay? And you also know that K, which is both the boundary of E, the collapsed part, and so that K, just look at K, is close to be is close to the area of the disk. So here there should be, yes, because I put a 1 here. The area of the disk. Okay. So if I put a 1 in front of K, it's like I'm putting a 1/2 in front of the wet part. Okay. So under these conditions, in a cylinder of horizontal radius half, there is no wet part. So under these conditions, and intuitively, it's the kind of thing you say, but this is obvious, right? Because if there is a wet part, it must look like a curvilinear triangle. But if it's a curvilinear triangle, then if I put the curvilinear triangle like this, then there is going to be a spike going up. And how do you do the epsilon confinement, right? Well, yes, and that's the idea. How do you prove it, right? So that's where these regularity theorems are delicate. So in particular, in the cylinder of radius 1/2, same height, K is just a smooth surface. There is no wet part. So you can use this theorem and the covering argument, okay, to prove that away from the so imagine now that KE is converging to a minimizer in Harrison-Pugh, S. Away from the singularity of S, S is regular by definition, okay? You're at a regular point of S. S is a smooth minimal surface. So there is a scale where it's very flat, and you can cover it at the scale, very flat in each cylinder. Now, K is converging there in Hausdorff. We need the Hausdorff theorem. So S was very flat, and the wet film is also very flat. That's the first condition. Then you're already at the convergence in area, and you're going to the area of S, but the area of S down there is essentially the area of a disk. So away from the singular set, I can find cylinders where these two things hold, and then this theorem tells me, okay, but then in half that cylinder, there wasn't no wet part. So this means that by a covering argument, the wet part has nowhere to go but towards the singular set of S. Okay? So, and at the end of the day is a sort, indeed, of epsilon regularity, is a regularity theorem at the end of the day, combined with a bit of this and that. Okay. I think that's enough. Okay, thank you so much for your attention.
Okay, so questions, comments?
Sorry. So this new Alencon is really nice in
Thank
a
you.
sense that I can feel like this can model a lot of more problems than a classical Alencon can do. For example, in classical Alencon, you cannot really make a puncture in the interface because it doesn't really make sense. Because there's from 0 to 1, you cannot really make a puncture. But in this picture, you can definitely do that. And maybe you can analyze like how much the puncture do you need to make it maybe you can think of the parabolic flow of this new Alencon, and then model how can you blow the soap bubble. Do you think this is like viable direction?
I don't know. This is mind blowing to me what you're describing. I'm not sure if I followed it, but yeah, maybe.
Like for example, you can you can imagine like flat surface of the soap film,
Yeah.
and then you know with a needle you just make a little puncture in your picture.
Okay.
You can definitely can do that.
Okay.
Yeah, and then see if it's energetically more
I think
convenient.
that so if you do punctured subfields, I think you're really going into these is the kind of thing you should study is more of an hyperbolic PD,
Mhm.
where the acceleration is given by the surface tension.
Yes.
So by the bound, so the kind of the acceleration of this hole, right? So
Yeah.
I'm not sure if
Yeah, of course, yeah, but still you can consider if the puncture will be greater if it's energetically favorable in your picture, right? In the just the given solution. So
okay. So one thing that, okay, maybe one thing I should have added. So when Novak, Restrepo, and Skorogobatova did the regularity theory, they actually did the regularity theory for, instead of W prime minus lambda V prime, you can put there not any nonlinearity, but a lot of them. So there are conditions, right? Including zero, nothing. So and so this means that they have an existence theory. The existence follows by our other results actually, but you have a regularity theory for something that is like they call them interestingly uh, the like surfaces of minimal capacity, right? Because you can solve essentially the Laplace equation with the constraint that the level set u equal 1 is doing the spanning. So sorry, like harmonic functions with the level set u equal 1 spanning a boundary. So I think it's a nice problem. And they have the regularity theory for that, and I don't know what kind of other properties may be studied there.
I see. Thank you.
Yeah.
Okay. Other questions?
Question for the physicists. What are they thinking about the spanning, and how do you choose it? Like the spanning, because here you have several choices.
Yeah.
So
For you, you mean? Well, for you, I think that the choice for you was like u equal 1. And at the end of the day, so u equal 1 is spanning, hoping that u is going to be regular, continuous, Lipschitz continuous, and u equal 1 makes sense pointwise everywhere. The clear choice is u equal 1. However, I mean, the reason why we ended up working with this thing is really technical. It's like, okay, now we have to prove the existence of a minimizer. So we had to relax this condition u equal 1 into this u star greater or equal than t and blah, blah, blah. At the end of the day, on a continuous function, this mass is equivalent to u equal 1 being suspended. Yeah.
Yeah, but I was thinking about the C.
The class C.
Yes.
Sorry. So this I don't know. So every time I've done, actually, this is interesting. I've done this. I talk about these models once at the New Jersey Institute of Technology and once at MIT. And in both cases, there was an audience with people doing material sciences or or applied mathematicians or applied mathematicians. And actually, it seems that that crowd is way more accepting and interested in the homotopic spanning condition than the mathematicians that of course are more conservative. And yeah, no, definitely I would say the physicists don't have any problem with this thing. I mean, it kind of yeah, makes sense to them, you know. And they definitely like these, they're definitely happy that you can do this wet film approximation and so on and so forth in the context of capillarity theory. So from the physicists, I've just heard happy people. How to choose it? Well, this is nobody knows how to choose it in the sense that nobody has really thought about that, I think, in terms of formulating a theorem. So I I have proposed several times the idea that the choice of C must be related to how you do the, dipping out of the seams. But how you formalize that, how do you describe this as a theorem, like given a wireframe and an angle of extraction from a basin. How do I compute the class C that I will see? Something like that. I don't know. It's something that one should try to formalize into a mathematical statement. I haven't, for sure. It's evident that something like that is happening. Now, I mean, okay. So, I don't know. It's a question. It's a very legitimate question. I can do that.
Maybe there are more questions? If not, let's thank again, Francesco. Okay, so we are ready for the last lesson of Francesca Tripaldi. Please.
Thank you. Right, so as I promised, today we're gonna do computations. So basically the idea is that since I gave a general idea of what the Riemann complex should be, I feel like it's only fair to give you an explicit example. So we're going to use the angle group as the example. So just a reminder of the Lie algebra. So this is a 4-dimensional real vector space, and the only non-trivial brackets are x1, x2 gives x3, and x1, x3 gives x4. So because we are relying on the homogeneous structure given by the stratification, just a quick reminder, I'm gonna have the weight of the two one forms that are theta 1, theta 2. These have weight 1. And then the weight of theta 3 is 2. And then the weight of theta 4 is 3. So this means that when you do the wedge, you have to sum the weight. So I'm going to have weight 2 for theta 1 wedge theta 2. So this is 1 plus 1. Then theta 1 wedge theta 3. This is the same as theta 2 wedge theta 3. So this is 3, which is 1 plus 2. And then theta 1 theta 4 and theta 2 theta 4. This is 4, which is 1 plus 3. And then theta 3 theta 4 is, so this is 5, which is 2 plus 3. So then we have 1, 2, 3. Then we have 1, 2, 4. And then we're going to have 1, 3, 4 and 2, 3, 4 as 3 covectors. So this is 1 plus 1 plus 2. So this is 4. Then I'm going to have 5, which is 1 plus 1 plus 3. And then this is 1 plus 2 plus 3, which is 6. And the volume covector, which is 1, 2, 3, 4. So this has weight 7 because it's 1 plus 1 plus 2 plus 3. Right. So this is the same as the homogeneous dimension of the angle group, the Hausdorff dimension if you're putting the Sub-Riemannian metric on it. And we're all happy. So we have a whole bunch of weights. So the aim of the game is to study the action of the D0 and then compute the cohomology of D0, which will give us fewer forms and hopefully fewer weights of forms, because if you remember, the problem was too many weights, too many homogeneous orders, and so on. Okay. So we are going to compute the action of the D0. So again, the D0 is the same as D acting on left invariant forms, which can be thought of also, this is the isomorphic to K vectors, K covectors, sorry. Right. So I just take the differential acting on these forms. So just a quick reminder, this is D of a theta I on acting on X, K wedge or comma XL. So this is minus theta I on the bracket. Since this coincides with D, and I know that the Leibniz rule holds for D, I'm going to just compute it explicitly for one forms, and then I'm going to extend it using the Leibniz rule, okay? So we had already computed this thing for the angle group, but just a reminder, I have that D theta 1 and D theta 2 are both 0. And then D theta 3 is minus theta 1 wedge theta 2. And D theta 4 is minus theta 1 wedge theta 3. And this comes exactly, so you literally see it dually as x1 bracket x2 gives x3. And x1, x3, this is a 2, gives x4. Okay. So now we're ready to compute also the action. So basically, okay, so let's do this for one forms. This means that the kernel of D0 on one covectors, let's say, this is the span over R of theta 1 and theta 2. But also I have, this tells me also that the image of D0 on two covectors, this is the span over R of theta 1 wedge theta 2 and theta 1 wedge theta 3. Because I have to shift one degree. Right. The fact that on functions I don't have brackets just means that the image of D0 on one covectors is simply the empty space, because if I do the D0 on a function or a constant in this case, it would be 0. So D0 on 0 forms is the 0 map. Okay, so basically this is what we need. Sorry, this, right? This and this is what we need to compute the space E0 on one covectors. So this, so it's the kernel of D0 intersected the complement, the orthogonal complement of the image of D0. The image of D0 is nothing, so I'm only interested in the kernel. So this is just the span over R of theta 1, theta 2. So we have the space of Riemann one forms. It's with coefficients in C infinity G. So E0 being the space. So this is the span over C infinity G of the same covectors. Okay, so we have the space of one forms. Now let's have a look at the weights. So actually this is pretty good. So what I've managed to do so far is to we got rid of theta 3 and theta 4. So we're only looking at two out of 4 forms. And also the collection of the weights, this is not standard notation, I'm coming up with this. The collection of the weights of E01, so the space of Riemann 1 forms, is just 1. This is the range of weights in E01. So I only have one weight. So I have theta 1 and theta 2, but they both have weight 1. Nice. Okay, we're very happy about this. Now we take a look at what happens for 2 forms. So on 2 forms. On 2 forms, I have to compute the action of the D0 on theta 1, theta 2, theta 1, theta 3, theta 1, theta 4, theta 2, theta 3, theta 2, theta 4, and theta 3, theta 4. Okay, so this is just, so we use the Leibniz rule, we said. So this is d theta 1 wedge theta 2 minus theta 1 wedge d theta 2. Both are 0 because d theta 1 is equal to d theta 2, which is equal to 0. So this is 0, which we were expecting because it's in the image of d0 as well. Is it okay? Yeah. Say it again. 2 out of 4 forms. We're left with 2 out of, so there are 4 1 forms. We look at it, yeah. It's, yes, yeah. We only look at the Riemann forms now. Yeah, it's easier then. Okay, so now we keep going. So we have d theta 1 theta 3 minus theta 1 wedge d theta 3. Right, so the first one is always 0, so we're left to look at minus theta 1 wedge theta minus theta 1 wedge theta 2. So this is actually 0 because theta 1 wedge theta 1 is going to be 0. As you would expect, because again, theta 1 wedge theta 3 was in the image as well. D theta 1 wedge theta 4 minus theta 1 wedge d theta 4. Again, d theta 1 is 0, so this is minus theta 1 wedge minus theta 1 wedge theta 3. 0 again. Nice. Yeah. Yes. Yes, so I can use the Leibniz rule. Yes. So then d theta 2 wedge theta 3. This is minus theta 2 wedge d theta 3. D theta 2 is 0. And then I'm going to have minus theta 2 wedge minus theta 1 wedge theta 2. So this is again 0. Then I have d theta 2 wedge theta 4 minus theta 2 wedge d theta 4. So this time I'm going to have something non-trivial because I have minus theta 2 wedge minus theta 1 theta 3. So minus, and then I shift. So I'm going to get another minus. This is minus theta 1 theta 2 theta 3. Then I'm going to have d theta 3 wedge theta 4 minus theta 3 wedge d theta 4. Okay, so this is minus theta 1 theta 2 wedge theta 4 minus theta 3 wedge minus theta 1 theta 3. So the second addend is 0 because I have theta 3 wedge theta 3. So this is minus theta 1 theta 2 theta 4. Right. So I have a kernel of D0 on two forms, two covectors, which is a four-dimensional space. So this is spanned by theta 1, theta 2, theta 1, theta 3, theta 1, theta 4, and theta 2, theta 3. And then I have the image of D0 on lambda 3 G star. This is a two-dimensional space. And so this is spanned by theta 1, theta 2, theta 3, and theta 1, theta 2, theta 4. Is it okay? I mean, it's long and boring, but it's Leibniz. Okay. So now we're ready to compute the space of Riemann forms in degree 2. So E0. Now we're going to do this on covectors for the moment. So this is the kernel of D0 intersected with the orthogonal complement of the image of D0. Now the image of D0 is on two forms, right? So it was here. It was this one that I'm looking at. So the image of D0 on two forms is theta 1 wedge theta 2 and theta 1 theta 3. So this means that this is going to give me the span of theta 1 theta 2, theta 1 theta 3, theta 1 theta 4, theta 2 theta 3, intersected with the orthogonal complement of the span of theta 1 theta 2, theta 1 theta 3, orthogonal complement. Still okay? Okay, so because of the way I chose this basis to become orthonormal, this is simply the span of, I'm going to list 2, 3 first and 1, 4. So this is a two-dimensional space. So what did I do here? So in this case, I managed to, so E0, 2, as in with smooth forms, not covectors this time. So this is the span over C infinity G of theta 2, theta 3, theta 1, theta 4. So I managed to get rid of, so this two covectors is a six-dimensional space. So I managed to get rid of 4 forms out of 6. Is this ideal though? This is not ideal because the weight of 2, 3 is 1 plus 2, so it's 3. And then the weight of 1, 4 is 1 plus 3, which is 4. Yeah, not great. I mean, we did our best, but I guess it wasn't enough. So we're not going to have a homogeneous DC for sure. But at least it's not like I'm going to have 6 different differential orders. I'm going to have just 2 because I start from a weight 1 and I end up with weight 3 and 4. So, yeah. And then finally, I'm going to have a look at the space of 3 covectors this time. So we're left with finally 3 covectors. So 3 covectors means I need to look at 1, 2, 3, 1, 2, 4, and then 1, 3, 4, and 2, 3, 4. And we're going to see that this is always 0. So this is the same as theta 1, theta 2, d theta 3. This is the same as theta 1, theta 2, d theta 4. This is the same as theta minus theta 1, wedge d theta 3, wedge theta 4, plus theta 1, theta 3, d theta 4. And then this is minus theta 2, d theta 3, wedge theta 4, plus theta 2, theta 3, wedge d theta 4. So first one is going to give me 0 because I have d theta 3 is 1, 2. D theta 4 is 1, 3, so I have repeated 1, so this is 0. D theta 3 is 1, 2. 1 is repeated 0. Plus theta 1, theta 3 repeated 0. So this is 0. Again, d theta 3 is 1, 2. 2 is repeated. And d theta 4, the 3 is repeated. So this is 0. So everything is 0. So this means that the kernel this time is everything. The kernel of D0 on 3 covectors. This is the space of 3 covectors. Okay. Right. The image of D0 on the space of 4 covectors is 0. Then this means that I have that E0 on the space of 3 covectors. So this is the kernel of D0 intersected with the orthogonal complement of the image of D0. So this is everything intersected with the orthogonal complement of the span. Now I have a look at the back. So the image of D0 on 3 covectors is 1, 2, 3, and 1, 2, 4. So this is 1, 2, 2, 3, and 1, 2, 4. So this gives me a 2-dimensional space, which is spanned by 1, 3, 4, and 2, 3, 4. So in this case, I had originally 4 forms, 3 forms, and I got rid of 2. Is this okay? So the weight of 1, 3, 4 is 1 plus 2 plus 3. So this is 6. And 2, 3, 4 is weight 1 plus 2 plus 3, which is 6. Okay, good. So this is nice. So I'm going to have problems on degree 2, but for the rest, I'm going to be fine. And the final thing, as you would expect, the volume form is a Riemann form. I don't know if you would expect it, but yeah. The volume form. So this is theta 1, theta 2, theta 3, theta 4 is in the kernel of D0 because the map is 0 after this. And I have no image of D0 to get rid of it. So this is E04. So just to summarize the situation, we found, so the space of Rham 1 forms. This is the span of theta 1, theta 2. The space of Rham 2 forms is 2, 3, and 1, 4. And then the space of 3 forms is the span of 1, 3, 4, and 2, 3, 4. And now the easier ones are 0 forms. So 0 forms is just the span over C infinity G of the constant. So this is just C infinity G. All the functions are Riemann 0 forms, right? And I'm going to have the volume form, so span C infinity G of theta 1, theta 2, theta 3, theta 4. So this is omega 4 of G. So just to reiterate, I'm going to have exactly the same as in the de Rham complex, just on functions and the volume. So in degree 0 and maximal degree. Then on 1 forms and 3 forms, I'm going to have a subspace which is homogeneous, both 1 forms and 3 forms. And then in degree 2, it's not nice, but it's okay. It's fine. So I'm going to have something. So in the picture that I have in mind, so if I have P equals to 0, P equals to 1, P equals to 2, P equals to 3, P equals to 4, P equals to 5, P equals to 6, and P equals to 7. And this is the degrees. So this is K equals 0, K equals 1, K equals 2, K equals 3, and K equals 4. I'm going to have C infinity G, right? If I want to do the span over C infinity G, so this is going to be the constant one. This is going to be theta 1, theta 2. This is going to be theta 2, theta 3. This is going to be theta 1, theta 4. 1 plus 3, yeah. Wild. So this, then I'm going to have 1, 3, 4, and 2, 3, 4. And then I'm going to have the volume form. So with the I need to find the arrows, the DCs that join this thing. It's going to have some DC, which is the sum of 2 operators. So the difference between 3 and 1 is 2, and then DC 3. And then I'm going to have a sum of DC 3, DC 2, and then DC 1. Right. Fine. So basically, the DC I'm going to find will look like this. So exactly in the same way that you would expect. So it's going to be the sum of these 2 operators. And then I'm going to have just homogeneous ones between functions and 1 forms, and between 3 forms and the volume form. This is always the case on a Carnot group. If I have 1 form, so they're always going to be horizontal. And because it's Hodge closed, we didn't see this, but the complement of a horizontal one form is always a codimension one form of weight capital Q minus one. Okay, so I'm always gonna have homogeneity in degree one and co-degree one. This is always the case, but in the middle, it's a problem. Right. And this is not enough. We need to find the DC. Yes. We need to find. We haven't computed it. We assume that. Yes. We have just found the forms. Okay. Yes.
The decomposition that is like E equal to 0 plus.
Yes.
I thought that this E2 was a member.
Nah. No, the decomposition comes in handy if you want to express the DC in terms of that. But no.
E2 wouldn't go. That increases
On the not on the same space. It increases the weight by the same amount, but it doesn't act the same. It's not the same action. And also the space is different. The codomain is different, yeah. Okay. Good. So we remember, of course we do, the expression for DC. So the DC was a pi E first. So we looked at the diagram that went E0, E, E, and E0. So we need to go pi E first, then we go D, and then we go pi 0. Okay. And this is it's the definition of DC. Okay. So this is pi E first, D, and then pi 0. Now, the horrible expression for pi E, when you start from E0, it's a little bit nicer. So it's the identity minus D0 inverse D. Now, I'm writing D, but because I'm applying it to E0 terms, right? So this D acts on E0, so i.e. a subspace of the kernel of D0. This is the same as saying D minus D0. So no? Yeah? So it's just, I'm going to write D, but don't expect to find a D0, okay? The D is always everything, okay? So it's D0. In this case, I have D0, D1, D2, and D3. Do I have D3? Yes. Do I have D3? Yeah. Then I'm going to have plus D0 inverse D minus D0, D0 inverse D. So this is why I'm saying the extra terms after are going to have D minus D0. So I'm doing exactly the same, even though it is presented as different, this D and this D minus D0, it's actually the same action, okay? Because otherwise, if I were to leave the D0 in, it's not a nilpotent operator. I'm just going back and forth with an identity. Okay, so this is pi E. Right. So to do this, we start from functions. Functions are easy. Also, we expect an order 1 operator, okay? So we do pi E on a function. So this is going to be a function, so the identity, minus d0 inverse df plus d0 inverse. I'm stopping it because I'm telling you that nothing will come after. Okay. Like if you start, nobody knows where it actually starts. I mean, at some point it will end, but you have to compute it. D minus d0 inverse df. Now, the nice thing, so that simplifies a lot here, is that we saw that d0 from functions, so from 0 forms to 1 forms, this was the 0 map, is the 0 map, which means that if I try to do d0 inverse, so that basically the image of d0 on 1 forms is 0. So if I have a 1 form and I try to do the d0 inverse, I'm projecting first on a 0 subspace. Is it clear? So I need to do a d0 inverse of the 0 map. Is it clear? So basically, when I end here, the whole pi e ends at the identity. This df is a 1 form. I try to do d0 inverse. This is going to be 0. And so this is going to be 0. So pi e on a function is just the function. d0 is invertible on the image of d0. d0 is a linear map. It's injective. So it has an inverse on the image of d0. The image of d0 is 0, is injective. So I have a d0 inverse on the image of d0. If the image of d0 is 0, I don't have a d0 inverse. It's going to be the 0 map, okay? So I need to project. So d0 inverse is always thought of as d0 inverse on the projection onto the image of d0. So yeah. Yes. On functions. Sort of. It's not really a sign, but yeah. Also, yeah, you can think it's so basically the image of d0 is equal to the image of delta 0 as subspaces. So if you need to project on that space and the image of delta 0 is 0, I'm projecting on. Yeah. And yeah. Yes. On between functions and 1 forms. d0 is an injective map always. d0 is 0, yes. On functions, yes. So if I'm trying to invert this, I don't get anything. It's the 0. So basically, I'm saying that it is a bijection between the image of. So there is an injection and a bijection between these two spaces. This is d0. So this, I can do this. I can have a d0 inverse. I can have a d0 inverse on the image of d0, only on the image of d0. If the image of d0 is 0, I'm projecting on a 0 space, so I don't have anything. Yes. 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 Is 0. it is yes, it ends up being a zero map, but you have to think of it as first I project on the image of D0, and then I do the inverse. That's the map. So yes. Because yeah. So this is to say pi e here is safe. It's just the identity. So I'm not moving anything with pi e. So I do df is simply d pi e f. So this is the differential. So this is x1 f theta 1 plus x2 f theta 2 plus x3 f theta 3 plus x4 f theta 4. Safe. Good. Now, what is happening here? So I'm not ending up on the space of Riemann forms because I only had 2 Riemann forms. I need to project. So I'm projecting pi 0 d pi e f as the projection onto the space of Riemann forms. Now, yes, I think we saw the definition of pi 0. Pi 0 is the identity minus d0, d0 inverse minus d0 inverse d0 on df. Again, exactly for the same reason as before, this term does not compute anything. That's a 0 term because d0 inverse is 0 on 1 forms. So I'm left to compute d0, d0 inverse. And that works like the projection of the 1 form on the image of delta 0. So the part on the orthogonal to the kernel of d0. So d0 on df, this is what? This is minus x3f theta 1 theta 2 minus x4f theta 1 theta 3. And then I do d0 inverse d0 df. I'm going to be doing this just, we'll see. So I'm doing exactly the same thing back. So it's x3f theta 3 plus x4f theta 4. So I didn't do much, actually. I just figured out which forms were on the image of delta 0 in the space of forms. So basically, I'm saying on the space of 1 forms, theta 1, theta 2, the span of this was the kernel of box 0, and then theta 3, theta 4 was the image of delta 0 on the space of 1 covectors. So these ones are in the orthogonal complement to the kernel of D0. So this is why if I do D0 inverse, this is the identity on this space. So it's just a projection of the part that I don't like. And then I'm left with just saying I have df minus d0 inverse d0 df. So I'm canceling out the parts of df that I don't like. So this is just x1 f theta 1 plus x2 f theta 2. Because I'm just removing these. This is this. And guess what? This is the horizontal differential, the the D1 that you see all the time, right? That you see. If you've ever seen Subramanian things, this is the differential that you do on functions, right? Horizontal gradient, thank you. Right. I'm not going to do the codifferential though. It's the horizontal divergence, right? But it's fine, okay? That will give you the sublaplacian on functions. So the sublaplacian on functions is exactly the Hodge Laplacian. I should use delta C dc on functions. So it is the Hodge Laplacian of the Riemann complex on functions. This is why it's nice. And this happens all the time, okay? So this is it doesn't just work for the Engel group, it works for all the Carnot groups. So it will always be a second order operator, and it's homogeneous, and it's hyperelliptic, subelliptic. Yes. Yes. Good. So we survived the Riemann differential on functions. Let's try to survive the one on forms. This is going to be long, okay? So brace yourself. Okay, so we expect, so expectations for DC. So DC is from 1 forms to 2 forms. I'm going to end up with a differential operator that is going to be a sum of an order 2 and an order 3. So I want DC, which is going to be an order 2 plus an order 3. So I need to get rid of the order 1 operators. Because if I do D, I'm going to have a D1, D2, D3. So no, I don't want any D1. So that's going to be cancelled out at some point. It's going to be cancelled out pretty fast. Okay, so yeah. From the information I have of the forms, the weights of the forms. Okay, so just a reminder from what I need. I have the space of 2 forms. So this is a 6-dimensional, sorry. I don't need this, I need this. So I'm going to have an image of D0 plus the kernel of box 0 plus the image of delta 0 on this. So this is the span of theta 1, theta 2, and theta 1, theta 3. So these correspond to theta 3 and theta 4 morally. Plus, I'm going to have 2, 3, and 1, 4. And then I'm going to have 2, 4, and 3, 4. Because I need to project, so it's going to be handy. I'm ready to take a 1 form. So I have F1 theta 1 plus F2 theta 2. So this is a arbitrary Riemann 1 form. And I need to do the pi e of alpha. So again, this is the identity minus D0 inverse D minus D0 inverse plus, sorry, D minus D0, D0 inverse D. of alpha. Okay, just to start, I'm gonna compute D0 inverse D of alpha. Because before it was a bit too easy, okay? So if I do D alpha, right? D alpha, I'm gonna have what? I'm gonna have x1 f2 minus x2 f1 of theta 1 theta 2 plus minus x3 f1 theta 1 theta 3 plus. So I'm going to have minus x3 f2 theta 2 theta 3 minus x4 f1 theta 1 theta 4 minus x4 f2 theta 2 theta 4. Did I put everything? 1, 1, 2, 1, 3, 1, 4, then 2, 1, 2, 3, 2, 4. That's everything, right? I need to do the D0 inverse of this thing. The D0 inverse is defined on the image of D0. So the only thing I'm going to have to do the D0 inverse is theta 1, theta 2, and theta 1, theta 3. So these two will contribute to this pi e, not the others. Yeah. It's in the image of D0. We had computed it before. Yeah. No, only the blue part is in the image of D0. Yeah. So if I do D0 inverse D alpha, then this is going to be minus x1 f2 minus x2 f1 theta 3 plus x3 f1 theta 4. Yes. But you can project D alpha on the image of D0. And that's going to be just the parts with theta 1, theta 2, theta 1, theta 3. Now, this is very easy because it's already an orthonormal basis. And it's easy. It is a projection. D0 inverse always has a projection. If I write D0 inverse, I'm projecting and then doing the D0 inverse. Yes. Okay. Now, do I have to keep going? So does it make sense to go and compute D0 inverse D minus D0, D0 inverse D alpha? And unfortunately, yes. So I'm left with this thing. Now, if I do D0 inverse D minus D0 of minus x1 f2 minus x2 f1 theta 3 plus x3 f1 theta 4. Now you see that if I do the d1 of theta 3, I'm going to end up with 1, 3. So that's still in the image of d0. So this is d0 inverse of minus x1 f2 minus x2 f1 theta 1 theta 3. Now I'm not going to write it. You keep going, but these are things in the orthogonal complement to the image of D0. So it helps to do the computation. It helps to figure out which ones are the forms in the image of D0 first. So at least you don't compute the whole differential. So you just end up where you need to compute. And so this is equal to x1 f2 minus x2 f1 theta 4. And that's the end of the pi e, okay? So the pi e of alpha, so this is alpha minus d0 inverse d alpha plus d0 inverse d minus d0, d0 inverse d alpha. So I remember what I was looking at. So it's f1 theta 1 plus f2 theta 2 minus, so this is a plus, x1 f2 minus x2 f1 theta 3 minus, and I put it all these together. So I have, no, I'm not putting this together. So this is x1 f2 minus x2 f1 minus x3 f1 theta 4. So a quick and easy check that you didn't mess up that much is that you have to end up with the first alpha. So I have the first alpha and something that has weight higher. It has some differential orders, some differentiation terms, and all the other forms that I'm adding are in the image of delta 0 on the one form, okay? Because this is the pre-image. The pre-image. It's in the image of d0 inverse. So it has to give you an image of delta 0. Also, you see that the differential orders of theta 3 are 1. Okay? And the idea is that you get a weight 2, so it's 1 plus 1, go in differential order 1 from alpha. Does it make sense what I'm trying to say? So theta 3, the weight of theta 3 is plus 1 with respect to the weight of alpha. And this is covered by the differential order. Yeah. And then I go plus 2 in the differential order. And it's the same as the weight, which is 1 plus 2, which is 3. We don't do negatives. Yes. We don't do negative orders. We don't minus anything. No, we don't like that. So the idea is that you're starting from a one form of weight 1, and you end up with a form of weight 2 by taking a differential of order 1. 1 plus 1 is 2. Yes. Yes. So it's plus 2, not minus 2. Yeah. No minus. We didn't do minus. Right. So basically, this is an easy way to check. I mean, if you have done the computations wrong, I'm sorry. Like, it's not. This is not going to save you, but the idea is that you're not messing up that badly. Right. So d pi e now. We're ready to do d pi e. Right. So if you, as you can see, I am gonna have a d0 here for the d. It's gonna be removed after, okay? But it's dd, okay? It's the whole of d. So I'm gonna have d of f1 theta 1 plus f2 theta 2 plus, I'm gonna leave it like this, there's d0 on the orthogonal complement of the kern of d0. I'm not gonna, it's just a quick notation, plus d minus d0 of the rest. So x1 f2 minus x2 f1 theta 3 plus, I'm gonna call this coefficient a. Okay, this coefficient is a and this is coefficient is b because it's long. So this is a theta 3 plus b theta 4. I'm gonna do the computation. Now, if you notice, I have d alpha. I already computed the d alpha. It was this one. Okay. So I'm gonna have the part of the d alpha that I had removed before, and I keep it. And then, so this is one crucial thing. So basically, doing this pi projection allows me to remove the image of d0 when I do the d alpha after. I hope this is somewhat clear. So if I do the d1, so I do the d1, x1 f2 minus x2 f1 theta 1 theta 2, then I have minus x3 f1 theta 1 theta 3 minus x3 f2 theta 2 theta 3 minus x4 x4 f1 1 4 minus x4 f2 2 4. This is d alpha plus the d0 of a theta 3 plus b theta 4. I'm going to leave it for the time being like this, plus the d of a plus b theta 4, the differential part of the, so this is plus x1 a theta 1 theta 3 plus x2 a theta 2 theta 3 plus minus x4 a theta 3 theta 4. Then I'm gonna have plus x1 b 1 4 plus 2b theta 2 theta 4 plus x3b theta 3 theta 4. Okay. Now, this is actually simplifying quite a bit already, okay? Because I look at the image of d0. I have the image of d0 here, here, and here. And I'm going to have it here. This is, so I had the Hodge decomposition. So this is an orthogonal decomposition. So the image of d0 deals with the image of d0. Then I'm going to have the kernel of box 0. Then I'm going to have the image of delta 0. So I'm looking at these things, right? This is exactly why I'm using pi e, basically. A was x1 f2 minus x2 f1. B was exactly x1 of x1 f2 minus x2 f1 minus x3 f1. So this is x1a minus x3 f1. Do you see where I'm going with this? This, I wanted to use another one. This term is introduced to cancel out the rest of the blue part. If I do the d0 of theta 3, this is minus theta 1, theta 2. So this means that d0 a theta 3 I'm going to use this. This is going to cancel out this. And then this is going to cancel out both this one and this one together. Because there is, when you do the d0, there's a minus coming out, okay? This is not a case. This is not by chance. It's how the PDE is constructed. So what I'm left with is everything I had when I was doing the D minus the part of the image of d0. So this I'm left with minus x3 f2 plus x2a theta 2 theta 3. Then I'm going to have the part with the theta 1 theta 4. So this is x1b minus x4 f1 minus, no, that's it. That's about it. Theta 1 theta 4. Then I'm going to have the theta 2 theta 4. So I'm going to have x2b minus x4 f2 theta 2 theta 4. And then I'm going to have x3b minus x4a theta 3 theta 4. Yes. Of this one. No, of this. Everything. Yes. So actually, so d pi e alpha does not belong to E0, because it doesn't, but it belongs to the orthogonal complement of the image of d0, because I managed to get rid of part of it. However, the part in the kernel that I like are these two. Okay, so this is where the pi 0 then comes in. So then I'm left to do pi 0 of d pi e of alpha. Again, this was d pi e of alpha. And this, can I just say this? This is a projection of the d pi e alpha on the kernel. So this is just getting rid of anything that I don't want. So this is minus x3 f2 plus x2 x1 f2 minus x2 f1 of theta 2 theta 3. And then, sorry, this is my plus x1 squared x1 f2 minus x2 f1 minus x1 x3 f1 minus x4 f1. Theta 1, theta 4. So I just made it explicit. So this is the DC. What did I want? I wanted a sum of two operators, one ending up on theta 1, theta 3, and one ending up on 1, 4. I did get that. Is the order okay? So the first one is homogeneous of order 2. That's okay. And the second term is homogeneous of order 3. Yeah? So it looks like it's something that I was looking for. So it's okay. Now, one very important thing to say about this is that each term is not D2. So if I were to start with alpha, alpha was F1 theta 1 plus F2 theta 2, the D2 of alpha, this is minus x3 F1 1 3 minus x3 F2 2 3, right? Even if I were to project this onto the correct space, so on the kernel, this, yes, it does appear, so there is going to be a D2 of alpha, right? I can see that there is an x minus x3 F2, but there is an additional term. So this is, if you've seen the magnificent second order operator on the Heisenberg group, this is exactly D2 minus D1, D0 inverse D1. And then you project it onto pi 0. And this is exactly the second order operator that you have here. So what do I mean by D2, D1? Exactly what I meant before when I was decomposing the D. This is the DC2. So you collect together all the terms that have the same differential order. Now, what is interesting is that using this decomposition, you can express any order, okay? So this, in general, this is going to be D3. So D3, you would expect the D3 here. It's x4 minus of f1. But this is going to be minus d1 d0 inverse d2 minus d2 d0 inverse d1 plus d1 d0 inverse d1 d0 inverse d1. So it is like a combinatorial thing that you collect in all the terms with a correct. So if it's, yeah, you see here, it's not a mistake. This is a plus. It depends on how many times you do the d0 inverse. But you collect in all the terms that have the same differential order, okay? And this is going to be the DC3. So there is a way to express this thing if you want to specify the order that you're looking for. So there are two ways of doing this, and they are exactly the same. So you either use the D2 minus D1, D0 inverse D1, and then you project, or you use the definition. Now, if you use the definition blindly, it's going to take longer. If you use the definition more or less the way we used it, so you kind of look for the image of D0, it's going to take exactly the same amount of time, okay? And it's a lot of time, but yeah. So this means that we have computed the DC, so the Rham differential from one forms to two forms. Now, I was going to do the one or two forms, but no, we're not going to do this. So we have 10 minutes left. The only thing I'm going to say regarding what you need to expect. So it helps out if you start by computing. So as what we said was, it helps out to compute first the action of D0 to understand how it works. You find the Hodge decomposition that is associated to D0. So you have the forms that on the image of D0, the forms that on the kernel of box 0, so the Riemann forms, and then the forms that on the image of delta 0, so that when you go and compute these projections, especially with the D0 inverse, it's easier. So you don't have to compute blindly the whole D. You look for the D that you're looking for, okay? And so if you want to go and compute the DC on two forms, have fun. So know what you're looking for, okay? You need to be looking for, if you start from a two form, the term that starts from theta 2 wedge theta 3 will have to have differential order 3. The part that starts from theta 1 wedge theta 4 will have to have order 2. And then this one is going to be so much easier, okay? As you would expect. This one, easy. I have, again, like before, I have the D0, which is the 0 map, so I'm not going to project anything, okay? So very easy. I'm going to have just the D1. Actually, this is actually just the D, just Z0 derivative. So this is the easiest one. So I would say the DC on functions and on n-1 covectors, easiest one. And then in the middle, it's a mess. Good. I think it's enough. Thank you very much.
Thank you, Francesca. And questions?
Yes.
And the scalar product that you have fixed, which one is the two forms, for example?
So, oh, you're generalizing it. So you're taking exactly the same scalar product, and then you treat this as a C infinity G module. So you're taking F theta 1, F1 theta 1, F2 theta 2, F3 theta 3. That's an orthonormal basis.
On this two forms? No.
On the two forms, it's the same.
Okay.
Yes.
Okay. That's
Okay.
Other questions?
So in general, this construction, so if you are also in other groups, you in a sense repeat this procedure as a kind of explicit computations.
Yes.
No shorter path. No. Okay.
So I mean, no. Okay. So it would be so nice if somebody at least were to tell you what the space of Riemann forms is. The problem is that this is isomorphic to the Lie algebra cohomology, and on nilpotent groups, it's a big open question on what is the Lie algebra cohomology of nilpotent groups. So nilpotent groups are not even classified. They're infinite.
Yeah.
And so there is no algorithmic way starting from like a lower dimensional nilpotent group how to get to the Lie algebra cohomology. Because there is an algebraic construction that gives you, starting from any nilpotent group of nilpotency step S, there is an algebraic construction that gives you any nilpotent Lie group of dimension 1 extra, so dimension +1, and nilpotency step +1. But there is no way to get not even the Lie algebra cohomology from the lower one to the higher one. So there is absolutely no way. Like, if you're given the nilpotent group, you sit down, you compute you look at the brackets, and then you compute the D0. It's just that. Also, in the algebra, people do that, and this is why they avoid nilpotent groups. But we cannot.
Thank you.
I was thinking about this sort of structure can be generalized in more generic sub-Riemannian manifolds, or because it relies strongly on the fact that we have like a sort of global frame, and so
Yes. So if it's an equiregular sub-Riemannian structure, then you're fine.
okay, makes sense.
There is also a way to generalize it to singular ones, like the Grushin plane. But basically, you're pointwise defining it as the Riemann complex of the Carnot group that you're seeing at the point.
So you expand and then
Yeah, like you look locally, and then you look at it,
wait,
and
so at the singular point,
you do the tangent cone.
okay, yeah, but that's not a Carnot group. I
The
mean,
tangent cone is always a Carnot group.
at singular point.
It is. Yeah, I understand what you
motion.
mean. There is a way to extend it that I have seen it done. I've never studied it, but it can be done. So also singular points can also mean just the Hausdorff dimension of the Carnot group changes. So for those, you're just doing it pointwise, what you end up with. For the singular ones, there is a paper by Eastwood and other people that you can look at. But yeah, I am not an expert on that.
Any other questions? If not, let's thank again
Thank you.
Francesca. Okay, so maybe we can start with the last lesson for this week. And please, Professor Young.
Thanks. So thanks for all being here. And I guess since this is the last lecture, maybe we can take an opportunity to thank the organizers, Giovanni and Valentino and Annalisa and Emmanuel. Thank you. It's been a very nice very nice workshop, and I hope that it goes just as well next week. So anyway, last time we talked about uniform rectifiability. And so today, what I want to do is I want to talk about using uniform rectifiability in geometry. And so there are two, so in order to apply uniform rectifiability to a geometric problem, there are kind of two things that you need to do. I mean, first, you need to figure out a way to take your problem, which probably isn't about something uniformly rectifiable. You have to figure out a way to take the problem you're interested in and turn it into a problem, into a question about uniformly rectifiable sets. And then two, well, you have to then prove something about uniformly rectifiable sets. So I wanted to today I wanted to give a couple of examples of how this can happen. So let me start with a problem of Peter Jones, which is called the analyst's traveling salesman problem. And so this is the following problem. Suppose you have a set. K in Rn, a bounded set. Is there a path or a connected set? It's essentially the same if you have a connected set that's essentially, let me finish the question. Is there a path or a connected set gamma such that the Hausdorff measure of gamma is finite? and gamma covers K. Right, this is inspired by the usual traveling salesman problem. The usual traveling salesman problem, you have a bunch of cities. You have a bunch of cities, and then you want to know what's the shortest path that connects all the cities. What's the shortest path that visits every city? The analyst's version is to say, okay, what if you have potentially infinitely many cities, or cities in some non-discrete setting? Can you visit all the cities with a finite path? And because we're interested in quantitative stuff, maybe we also want to estimate how long a path you need if it is finite. So Jones stated this in terms of connected sets or paths. It's essentially the same thing, because if you have a bunch of points and you have a connected set that connects those points, then you can turn it into a path. You can say, okay, I'm going to start here, I'm going to go here to here, and then backtrack, and then go on to the next place. And that at most doubles the length, because maybe you go out and back, but you don't take any particular road more than twice. So is there a path or a connected set such that the measure of the path is finite and it contains K? Clearly, the Hausdorff measure of K being finite is necessary, but not sufficient. You can construct examples. You can construct plenty of examples of sets with finite one-dimensional Hausdorff measure where you can't cover them by a path. But one that's familiar, one that we saw last time, is the four corners Cantor set, right? You take a square and you replace it by its four corners, and then you replace each of those by the four corners of those squares, and then you take the limit and you get a Cantor set. And this is the four corners Cantor set has finite Hausdorff measure, but can't be covered by a curve. Right. And so this problem actually, this problem was, Jones worked on this problem before the development of uniform rectifiability, and his solution to this problem was part of the motivation for uniform rectifiability. What Jones did was he found a sharp condition for when you can do this. And let me see, so I need a little bit of notation to state the condition. So let's define a dyadic interval is an interval of the form a plus, interval from a times, what do I want? A dyadic interval, so a over 2 to the k to a plus 1 over 2 to the k, where a and k are integers. A dyadic cube in Rm is a product of m dyadic intervals of the same length. And if Q is a cube, I'm going to define the following. I'm going to define the length of Q is the side length. I'm going to define, I want to define for all rho greater than 0, rho Q is the concentric cube with the length, the side length of rho Q is equal to rho times the length of Q. And then for K, a subset of Rm, I'm going to define omega sub K of Q is the diameter, is the radius of the smallest cylinder containing the intersection of K with Q. Right. The idea. So for instance, if K is this four corners Cantor set, and I take a cube like this, what's the smallest cylinder that contains the intersection of the set and the cube? The smallest cylinder is this strip like so, and so omega of that cube is that distance there. Right, so it measures. This is the same, or this measures the same sort of thing as the beta numbers we discussed yesterday. And in fact, we're just going to use this to define beta infinity. We're going to let beta k infinity of q to be omega kq divided by L of q. So if q is a straight line, this is 0. If q is, all over the cube, then the largest cylinder, the smallest cylinder is just going to be like that. And then omega is going to be, what is that? That's half the side length of the cube. Omega is going to range from 0 to 1/2. Okay? So, oh, and let me add one more bit of notation. Let's let D be the set of dyadic cubes. Then Jones proved the following. Jones proved this in dimension 2, and then it was extended to arbitrary dimension by Okikiolu. So we have two parts. If gamma in Rm is connected, then the sum over the dyadic cubes of beta gamma infinity of 3q squared times L of q is a lower bound for the Hausdorff measure of gamma. So this is very similar to the strong geometric lemma integrals that we talked about yesterday, with a couple of small differences. And the differences are, so one, we're summing over dyadic cubes here. We're not taking an integral over all balls. We're summing over dyadic cubes. And so the reason for this 3 here, the 3 is arbitrary. The 3 could be any number bigger than 1. The reason you need this change here is because if you're summing over dyadic cubes, well, the dyadic cubes form a tiling of Rn. And so if you had some set which had a corner right at the boundary of a dyadic cube, well, then you take this dyadic cube, you get beta number 0. You take this dyadic cube, you get beta number 0. You don't see the corner. And so we have to expand the cubes to make sure that we see every point. So instead of summing over beta numbers of the cubes, we multiply the cubes by 3, and then those 3 by 3 cubes cover the whole space, and they overlap enough so they see everything in the space. So that's one difference. Another difference is that, well, this sum and the integral don't quite translate to each other, except if gamma is Alforth regular. If gamma is 1 Alforth regular, remember what that means. That means that for all x in gamma and r less than the diameter of gamma, the intersection, the Hausdorff measure of the intersection of gamma with the ball of radius r around x has measure about r. If gamma is L force 1 regular, then we can replace this integral. We can replace this sum by an integral, and we get the integral from 0 to infinity of the integral over Rm of beta gamma infinity of xr squared dx. Sorry. Wait. This is already an integral over Rm. I want to turn it into an integral over gamma, and if I do that, then this power, this length term can't disappears, and we get an integral like this. Oops, and I've lost room for the other side of the inequality. And this is exactly the integral that shows up in the strong geometric lemma. So in the case that gamma is L force 1 regular, then this sum just becomes the integral that shows up in the strong geometric lemma, and this says that the integral that shows up in the strong geometric lemma provides a lower bound for the Hausdorff measure of gamma, right? So this is half of this theorem. This says that if you do have a connected set that covers K, then K has to satisfy this condition on its beta numbers. Because if you can cover K by some connected set gamma, well, gamma satisfies this condition on its beta numbers, and the beta numbers of K are going to be smaller than the beta numbers of gamma. It's okay so far? Yeah? Yeah. So just the upper bound in the density, really. Yeah. Yeah. The second half, conversely, if K in Rm is bounded and it satisfies this inequality, the sum over the dyadic cubes of beta K infinity of q square 3q square LQ. If this is finite, then there exists a connected L, or a connected gamma, such that gamma contains K, and the measure of gamma is less than a constant times the diameter of K plus this sum over the dyadic intervals. So on one hand, if you can cover it by a connected set, then it satisfies this inequality. Conversely, if it satisfies this inequality, then you can construct some connected set that goes over the whole K. Is this okay so far? And again, just like before, this is not quite the same as the strong geometric lemma that we saw yesterday. But if K is L force 1 regular, then this double integral, or we can replace this sum by this double integral. So like I said, this was done before the development of uniform rectifiability, but it was a big influence on the development of uniform rectifiability because it essentially has this strong geometric lemma condition before before uniform rectifiability, right? And so yeah, so this is a bit. It's a complicated sum. It's a relatively complicated theorem. The way that I would recommend thinking about it, the way that I would recommend looking at it is to try this. Try using this to show that the four corners Cantor set, or even iterations of the four corners Cantor set, do not have big pieces of Lipschitz images. Because this basically gives you a quantitative estimate of how much of the four corners Cantor set, or how much of these 4 to the I squares of side length 1 over 4 to the I, how much of that you can cover by a curve of length L. Okay, so I would like to go into more detail about this, but I have a limited amount of time and a lot of stuff I want to cover, so I'm just going to skip straight to the reason that I wanted to talk about this question, the reason that I wanted to talk about this theorem is because I wanted to talk about a particular, I wanted to talk about the proof. So like I said, Jones proved this in dimension 2, and then it was generalized to higher dimensions by Okikiolu. And like it has two parts. It has this one part where you're trying to find this bound on this lower bound on the Hausdorff measure of a set in terms of the strong geometric lemma. And it has this other part where, given a set that satisfies the strong geometric lemma, you want to find a connected set that covers it. And so the second part is the second part is a construction. Basically, you look at various dyadic cubes containing your set, and then you say, okay, I'm going to take this cube and divide it into smaller cubes, and I'm going to draw extra lines between these pieces until eventually, after I've processed all the dyadic cubes, what I'm left with is a bunch of lines connecting all the points in my set. So that is that part is a construction. This part is a little bit stranger, because this says that if you have a connected set, then you get a lower bound on its Hausdorff measure in terms of the strong geometric lemma. How do you prove that? Well, Jones's proof used complex analysis, which is why it only worked in dimension 2. Jones's proof used complex analysis, and in particular, it used the following lemma. So let me define a Lipschitz domain in the complex plane is a set, is the open set bounded by a curve. Sorry, let me just check make sure I get my notation right here. Is the open set is an open set of the form the set of points r e to the I theta, where r is less than some function of theta, where f is Lipschitz, let's say C Lipschitz, and f, the values of f are between C, let's say C inverse and C for some C greater than 0. The idea of this is that these sets are very nice. If if I have a function f that satisfies these properties, its Lipschitz constant is c at most c, and its values are between c inverse and c, then the boundary of that set, this set is basically defined in polar coordinates. The boundary is a set of points f of theta comma theta, and then the curve around that boundary is a bi-Lipschitz curve. This condition and the Lipschitz condition imply that the speed of that polar curve is bounded above and below. And so so domains like this are bi-Lipschitz equivalent to the circle, to the disk. I guess. Oh, sorry. Sorry, I should add one more thing because I want everything to be scale and translation invariant, and that is not quite true of what I wrote. So is a scaling or translation of a set of this form. So for instance, squares are Lipschitz domains. Any square in any size, any rotation is a Lipschitz domain. It's okay? Then Jones's lemma is the following. There exists a C greater than 0 such that for any S contained in C, a bounded open set, a bounded simply connected open set, there is a Lipschitz curve gamma such that every connected component of S minus gamma is a C Lipschitz domain, and the total length of the boundaries of these countably many of these connected components, the total length of the boundaries of these connected components is at most C times the length of the boundary of the original. Okay, so this is a decomposition where you can take an arbitrary, potentially very complicated open set, just any bounded open set, bounded simply connected open set, and decompose it into a union of Lipschitz domains where the total length of the cuts in that decomposition, the total length of the boundaries of those Lipschitz domains is not any bigger than a constant times the boundary of the original set. So for example, the Koch snowflake. If you take a triangle and you glue a triangle on the edges of that, and then you glue smaller triangles on the edges of that, right? If you draw the von Koch snowflake, this is not a Lipschitz domain, right? Okay, sorry. I guess I should. So let's for let's say 10 iterations. Right? Because I want it to have finite boundary at the end. So I'm going to take the interior of the 10th iteration of the von Koch snowflake. This is not a Lipschitz domain because you can't write it in polar coordinates in this form, but it has a decomposition into Lipschitz domains, which is exactly these triangles that you use to make it. Each of these triangles is a Lipschitz domain, can be written in polar coordinates. And furthermore, every time you add one of these triangles, so you start out with, maybe maybe you start with a unit triangle. So so you start with a triangle of boundary 1. In the first iteration, you add a triangle, another triangle, another triangle. Those are going to be parts of my decomposition. So that adds total length. This has perimeter 1, perimeter 1, perimeter 1. That adds total length 3 to the total length of the decomposition. But it also adds 1/3 to the length on this side, 1/3 to the length on this side, 1/3 to the length on this side. The length of the snowflake goes up by 1. And the same thing happens whenever you add any triangle of side L. What does it do? It increases the total length of the decomposition by 3L, because 3 sides each of length L, and it also increases the length of the snowflake by L, right? You take one side of length L and you replace it by 2 sides of length L. So no matter how many triangles you add, it still satisfies this property. No matter how many triangles you add, each triangle adds to the total length of the triangles and adds a comparable amount to the boundary of the set. So they're both increasing at the same rate, and so you get this bound here. Does that make sense? Yeah. Oh, sorry. Where SJ? Every connected component, the connected components of the set minus this all these cuts. More questions? So yeah, so for the Koch snowflake, this is very straightforward. The question is, how do you apply this to an arbitrary bounded open set? Well, yeah, I don't have time to cover. Yeah. Yeah, exactly. This next step here. So to prove this, yes. Yeah. This is not even a sketch. This is just the first step of the proof. But the way he does this is where he uses complex analysis. S is a bounded, simply connected open set. So by the Riemann mapping theorem, there is a conformal map from the disk to S, be a Riemann mapping. We take that disk and we divide it up into pieces. So maybe a center circle like this, and then you have, maybe this has radius 1/2, and then you have radius 1/4, or sorry, 3/4. So maybe so this distance is 1/4, and then we slice that up into a bunch of squares, and then we add on another ring where this distance is 1/8, and then we slice that up into a bunch of squares where each of the arcs from the previous ring gets split up into 2, and so on and so forth. We just keep on, we construct infinitely many annuli with radius 1 minus 2 to the I, and then we slice up each of those annuli into little, basically rectangular regions. What Jones does is he says, okay, well, if this map is nice enough, if we have some of these regions, maybe this region and this descendant and these descendants, if I have a bunch of these regions where the derivative of f prime is close to constant, if I have a bunch of these regions where f prime is close to constant, well, then what's the image of this collection of regions? It's some rotation and some rescaling of that set, plus a little bit of error. But I drew that badly. What is it? 1, 2, 3, 4, 5, 6, 7. Okay. It's some rescaling and translation of that set. And so if you can take sets like this and divide them up into Lipschitz domains, then the image under the conformal map is also going to be divided up into Lipschitz domains. And so then you can use use some estimates on the derivative of a conformal map to try to say, okay, I can usually collect a lot of rectangles like this together into one big region made of a lot of rectangles where the derivative is close to constant. The image can be decomposed, and so the main idea of the proof is to find regions like this. Okay. I'm not going to go into detail about this because there's a lot of stuff to cover, but Jones has a paper about this called the traveling salesman problem and rectifiable sets, and it's a very nice paper. So, is this okay so far? So the reason I bring this up is because this is a nice strategy. This is a strategy that can be applied more generally. Because what are we doing here? We take an arbitrary set S, or some very. We take an arbitrary set S. We decompose S into nice regions. In this case, when I say nice regions, these are Lipschitz domains. The boundary of S is a bi-Lipschitz image of a disk, and you can show, it's not so hard to show that, well, if a set is a Lipschitz domain, then you can break it up into a bunch of Lipschitz graphs, into a bunch of graphs of Lipschitz functions. And then because you can break it up into a bunch of graphs of Lipschitz functions are uniformly rectifiable. They satisfy Doron-Soros theorem. And so the sets that we break this up into, these Lipschitz domains, are uniformly rectifiable. Jones wouldn't have said it this way because uniform rectifiability hadn't been invented yet. But in retrospect, we can describe this procedure like that. We take an arbitrary set S, we decompose it into uniformly rectifiable pieces, and then we use these pieces to prove the theorem we're interested in. In the case of Jones, the way that works remember the goal here. The goal was that we have some arbitrary connected set. So maybe it's like, it's a bunch of lines. We have an arbitrary connected set with finite Hausdorff 1 measure. How do we apply Jones's theorem here? I shouldn't have drawn this so large. I'm going to need a little more space. We have our arbitrary connected set. What do we do to apply Jones? We draw a circle around the set. We draw a line from the set to the boundary of the circle, and then we say, okay, each of the regions in the complement of this picture is a bounded, open, simply connected set. So each of the regions in the complement of this picture I can decompose the interior of the Koch snowflake into triangles. I can decompose the exterior of the Koch snowflake into Lipschitz domains. The total length of those Lipschitz domains is bounded in terms of the measure of my original set. And so if you can prove this beta number inequality for the Lipschitz domains, that leads to a proof for your original set. So for example, prove the traveling salesman problem inequality for Lipschitz domains. And then extend to the boundary, and then extend to the original boundary of S. Okay. Is this clear so far? Are there any questions about any of this so far? Yeah. No, yeah, go ahead. Okay, okay. But yeah, so this is a strategy you can use to apply uniform rectifiability to geometric problems. You take your original object, you decompose it into uniformly rectifiable pieces, and then you use those pieces to prove your theorem. And this can generalize. So let me try to show you some ways to generalize this strategy. How am I on time? So, for example, we can do a higher dimensional analog of this. You can show that if you can show the following. Let S be a subset of the unit grid. So let S be a union of cubes in the unit lattice in Rn. This is a little bit specific. The reason I'm saying it's a union of cubes is because I need some local regularity. I need to know locally, if I look at very small balls, the set is very nice. So I'm going to get that by saying that S is just a union of cubes in the unit lattice. Then there exist sets A1 up to AN. Also unions of lattice cubes. Such that for all I, the boundary of AI is uniformly rectifiable, all with uniform constants. And we don't have quite as nice a decomposition as this. We have that the characteristic function of AI, or so the characteristic function of S is the sum of the characteristic functions of the AI with some signs. So instead of saying, you can write S as a disjoint union of a bunch of Lipschitz domains, here we're saying we have some set A, or sorry, you have some set S, and then we can just progressively cut off pieces of S or glue on pieces of S, so that every time we glue on a piece or cut off a piece, that piece is uniformly rectifiable, and we eventually build the whole set. And one more condition, and the sum of the measures, these are in in Rn. Let me make that an Rm so that that's a different number. And the sum of the measures of the boundaries of the AIs is less than a constant times the measure of the boundary of S, right? We need that last condition because otherwise I could just take, whatever my set S is, it is a union of, it's a union of lattice cubes. And so, for instance, I could take my decomposition to just take each one of these lattice cubes and call that a decomposition. The reason that we're not allowed to do that is because then the total boundary of all those lattice cubes could be enormous compared to the boundary of the original big set. So this is a sort of analog of Jones's theorem. Is this okay? Are there any questions about this? Yeah? There's a universal, so there's some universal C depending on just M and N, just on the dimension. More questions? So, so this a priori, this doesn't apply to, arbitrary sets. But what you can do is you can imagine, say I wanted to apply this to the circle. I can't write the circle as a union of unit cubes. But what I can do is I can take a very fine grid, just take a very, very fine grid, take all the cubes in that very fine grid that intersect the circle, and use that as my set. Because all of these notions are scale invariant. Uniform rectifiability is scale invariant. This notion of a decomposition is scale invariant. This condition about the total length of the boundaries is scale invariant. And so if I wanted to apply this to some arbitrary set, what I can do is I can approximate that set arbitrarily closely by some grid of cubes, and then use that and then use those cubes. Okay? And so the proof actually has some similarities to the picture for the Koch snowflake. The proof relies on a theorem of David, which says that so let me give a definition first. So the proof actually relies on a theorem of David about SEMS surfaces. A SEMS surface, a SEMS surface sigma in Rm is a so an epsilon SEM surface is a surface, and let's say that it is m-1 dimensional surface, which is L-force regular, which is L-force regular with constant epsilon, and with the property that for all x in the surface and r greater than 0, maybe let's say r between 0 and the diameter, there exists the ball of radius r around x minus sigma contains two balls of radius epsilon r in different components. So the picture the standard picture is you have some surface, some codimension 1 surface, so that if you take a point and you take a ball around that point, then you can find a ball of radius epsilon r on one side and a ball of radius epsilon r on the other side. Right? This is another scale invariant way of saying that a surface is nice. The sort of things that this excludes are cases when you have, say you have a surface and it's got a very pointy cusp like that. Then if I take a point over here, and I take a big ball around that point, then I can certainly find a ball of radius epsilon r outside on one side of the surface, but I can't find a ball of radius epsilon r on the other side of the surface. So it captures a lot of things. One of the things it captures is that your surface can't have cones that are too pointy, which is a reasonable thing to ask. Then David showed SEM surfaces are uniformly rectifiable. So if we want to prove this decomposition, here's an algorithm. First, if sigma is already a SEM surface, sorry, I got that backward. If the boundary of S is already a SEM surface, we're done. Let A1 equal S, and then we're done. Otherwise, there has to be some smallest cube. Let Q be the smallest cube. And let's say Q, let's let Q be the smallest cube centered on the boundary of S, such that the boundary of S is not a SEM surface inside Q. Oh, so I guess I should say I should fix a constant here. So fix some small epsilon greater than 0, and so if the boundary of S is already SEMS, we're done. Otherwise, if it's not SEMS, there has to be some smallest ball where there's a problem. What happens in that smallest ball? Well, there are a couple of possibilities. In order to be a SEM surface, you need to be L-force regular with constant epsilon, and you need to have two balls, you have a ball of radius epsilon r on both sides. So why isn't the boundary of S intersect Q SEMS? Well, one possibility is that it fails to be L-force regular, either because it is too dense, which is to say that the measure of, I'm going to write this measure as just absolute value, just because we'll see it a lot. Either it's too dense, which is to say that this intersection is bigger than epsilon inverse times the length of Q to the m minus 1. It is too sparse. This intersection is less than epsilon times length of Q to the m minus 1. Or there's not enough room on one side. there's not enough room on the inside. S is too small, which is to say that the measure of S intersect Q is less than epsilon times the measure of the measure of Q. It could be that there's not enough room on the other side. So Rm minus S is too small, which is to say that the measure of S minus, or Q minus S is less than epsilon times the measure of Q. And you can show that if these conditions are all satisfied on Q, and if these conditions are all satisfied on all the smaller cubes inside Q, then it is SEMS. Maybe not epsilon SEMS, but maybe epsilon prime SEMS. So otherwise, is epsilon prime SEMS on Q. So yeah, so if the boundary of S is already SEMS, we're done. Otherwise, we find the smallest cube that gives us a reason for it not to be SEMS, either because it's too dense, or too sparse, or it's too small, or S is too small, or S is too big. Any of these is a reasonable reason for why it might not be a SEMS surface. But each of these gives us a way of adding another set to the decomposition. Because what are the possibilities here? So if we have some cube Q, where S, the boundary of S is too dense, if there is too much of the boundary of S, well, one thing we can say about this is that this is not a minimizing surface. It's too big. There's an obvious competitor, which is you just take, instead of taking, I should have drawn that a little more simply. If I have some set like this, where here's my set S, I know that this is not a good competitor for a minimal surface because I can replace this. I can just delete all of S inside that cube and get something where the boundary is just entirely along the cube and the boundary is smaller. Likewise, if the set is too sparse, well, actually, if the set is too sparse inside Q, then by the isoperimetric inequality, either S is very small inside that set, or S is very big inside that set. So if S is in the second case, well, then we can pass to either the third case or the fourth case, depending on which side makes up the majority of Q. But in those cases, if S is too small or too big, if S is, if you have some picture like, maybe S is very small, or maybe S is very small like this, or if S is very small, then again, this fails to be a minimal surface. And there is an easy competitor, which is just erase all of S inside the cube. This takes a little bit more work to show because you have to be a little bit worried about, if I have something like that, it's not immediately clear that you can that it's not minimizing. But in those cases, what you can do is you can make your cube a little bit bigger or a little bit smaller. And remember, the cube is centered on something in the boundary, so there has to be something inside. Right. So in any of these cases, S, the boundary of S is not minimizing inside Q. So let's let I guess this is so let's let S prime be either S union Q or S minus Q, depending on which case we're in. Then the measure of the boundary of S prime intersect Q is less than or equal to, well, strictly less than, because it's not minimizing, and we've just replaced it with something smaller than the boundary of S intersect Q. And in fact, we can do better than this. The difference in these areas is at least, say, 1/2 times, the difference in these areas is at least, say, 1/2 times the area of Q intersect the symmetric difference. Symmetric difference, I'm going to write it like delta, the symmetric difference between S and S prime. Right, that symmetric difference is either S intersect Q or Q minus S, depending on which case we're in. So let this AI be the symmetric difference. So every time, so if we find a cube where it fails to be a SEM surface, we get another element of our decomposition, and then we repeat the process. If S prime is SEMS, we're done. Otherwise, we find the smallest cube where it fails to be SEMS. It falls into one of these 4 cases. Each of these 4 cases gives us a way to modify it to make it a little smaller. And so we can repeat to get an S double prime where the area of the boundary of S double prime is even smaller and smaller and smaller. Every time we do this, we are adding or subtracting some set AI, so this satisfies the decomposition property we wanted. Every time we do this, the area decreases, so we end after finitely many steps. Furthermore, the area decreases by a constant times the area of the new piece in the decomposition. Every time we do this, the area decreases by some constant times the area of the new piece in the decomposition. So you can write the total area of the original as a telescoping series. The terms in the telescoping series are bounded by the pieces in the decomposition. And so the total area of the pieces in the decomposition is bounded by the total area of the original surface. So basically what this does is it takes some complicated object. You know, if I take some surface, you know, just say I take a baguette. If I take a baguette, then this is not a SEM surface. But what this does is it says, okay, find a cube where it's not a SEM surface. Find a cube at one of these corners where it's bad, and just and then use that as the first piece in the decomposition. So we cut off that cube. We get a smaller surface, we repeat the process. We find a cube where this is bad, we cut off that cube. We find a cube where this is bad, we cut off that cube. We find a cube where this is bad, we cut off that cube until we end up with something that is a SEM surface. And you can do the same thing with more complicated objects. You could do, you know, if you have a dumbbell with 2 big pieces on either side and a cylinder in the middle, you can do the same thing. You find a piece where it fails to be a SEM surface, you cut off that piece, and you repeat that until you're left with pieces that are SEM surfaces. Does that make sense? So that's that's how we can, so that's a way to construct a decomposition like this. We can take a arbitrary open set, approximate it by something made out of cubes, and then decompose those cubes into a sum of uniformly rectifiable pieces. Any questions about this so far? So this is part of, the application of this is a project I worked on with the sophomore application. We can do the same thing, almost works. In the Heisenberg group. If you have a surface made up of fundamental domains, or if you have an open set made of fundamental domains of the Heisenberg group, then you can decompose it into a sum of uniformly rectifiable pieces. And then you can use, you can analyze those pieces. You can prove sharp bounds on embeddings of the Heisenberg group. In fact, any of the Heisenberg groups into the Banach space L1. It's okay so far? Oh, time, 20 minutes, okay. So that's codimension 1. That's a picture in codimension 1. It turns out that you can also generalize to higher codimensions. You can show that if T is a cycle in the unit grid, and let's say a D cycle in the unit grid in Rn with Z mod 2 coefficients, a cycle with mod 2 coefficients is essentially the same thing as a d-dimensional surface. So this is essentially the same thing as a d-dimensional, not necessarily oriented closed surface. Then there exist Z mod 2 cycles, again, A1 up to A K, such that each AI is supported on a uniformly rectifiable set with uniform coefficients, with coefficients depending only on dimension, only on D and N. And the same volume bound as before. Sorry, there's just Z2 cycles and they decompose the original and they satisfy the same about volume bound as before. The sum of the mass, the sum of the areas of those pieces is less than a constant times the area of the original. So basically now you want to think about the same sort of thing as before, but now we have something we can apply to say I draw, oh geez, I forgot that I was going to have to draw this. Say I draw a Klein bottle. Sorry. Say I draw a Klein bottle with a you know, what's a Klein bottle? You have a cylinder, and it comes around in R4 with a twist, and there it glues on with a twist, right? So you have a Klein bottle like this, which is embedded in R4. I want to be able to decompose this as a sum of smaller cycles that are all uniformly rectifiable. This fails to be uniformly rectifiable mainly because of this long neck. But you can do the same sort of thing as before. You can say, okay, I'm going to take this long neck, I'm going to decompose it into a whole bunch of little round cylinders, and then I'm going to write my Klein bottle as the sum of all these little round cylinders, the sum of all these little round cylinders, and then what's left is this sort of bulb, but if I take out all those little round cylinders, that bulb is just a sphere. So I can decompose it into nice, uniformly rectifiable pieces. And this picture looks very, very similar to the pictures we were drawing before with decomposing dumbbells and baguettes and so forth. And in fact, you can use a very similar algorithm. Again, if the support of T is uniformly rectifiable, we're done. Oh, sorry, I need one, before I can describe this, I need one, oh shoot. I need one definition before I can do this. So how do we construct this decomposition? Well, the first thing we need is a good source of uniformly rectifiable sets. Previously, we got our source of uniformly rectifiable sets from this theorem of David about some surfaces. Now we're going to use a different theorem of David and Sem's, which says that any quasi-minimizing set in Rn is uniformly rectifiable with constants depending on, let's say it's C quasi-minimizing with constants depending on C, where by a C quasi-minimizing set, I mean that sigma is C quasi-minimizing if for any bounded U and any homomorphism, not even a homomorphism, any map F from U to U, which fixes the boundary of U pointwise, this definition is analogous to some of the definitions of minimizing sets that Francesco talked about and that other people talked about this week. I want to say a set is minimizing if whenever you apply a compactly supported deformation, the area can only go up. A set is quasi-minimizing if whenever you apply a compactly supported deformation, the area might go down, but it can't go down too much. It can't go down by more than a factor of C. So for any compactly supported deformation, I want that the measure of f of sigma is greater than or equal to 1 over c times the measure of sigma. Does that make sense? Sorry? Yeah, 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 I'll write that, yeah. Yeah. Does that make sense? One of the things we learned this week was that minimizing sets have various rectifiability results. Minimizing sets have various regularity results. David and Fems proved that, in fact, those regularity results carry over to quasi-minimizing sets in a way, that a quasi-minimizing set is uniformly rectifiable. I mean, this is not as nice as, saying that a minimizing set is smooth away from some singular set of smaller dimension. This is a much weaker notion, but sometimes it's all you have, because there are lots of examples of quasi-minimizing sets. If I have a set like this, which is just a zigzag, then this is quasi-minimizing, because it's certainly not minimal, but if I apply a deformation inside a bounded set, the best I can do is I can replace that set by a straight line, in which case the length goes down by a factor of 2, say. Okay? But given this, we can prove the theorem. If the support of the original object is C quasi-minimizing, we're done. Otherwise, find the smallest set and the smallest deformation be the smallest set such that if it's not quasi-minimizing, then there's some smallest set where f of, what did I say, support of t intersect u has a lot less measure than the support of t intersect u. Let t prime be the image of t under this deformation. I mean, I guess I should say, yeah, so where f bar Rn to Rn extends f, and then let's let AI be the difference, t minus t prime. Then you can show this difference is kind of poorly behaved, because t minus t prime is basically the part of t that was inside this set u. And so the part of t that's inside u, well, we already know that there's some deformation that shrinks it by a factor of at least c. But the other thing we know is that if you take any smaller set, you can't shrink that by a factor of c. So there's a deformation that shrinks this by a factor of c, but there's no deformation that shrinks it by a factor of 10c, because otherwise you'd lose minimality. So A prime isn't quite a quasi-minimizer, but it's close enough that you can say that A prime is also the support of A prime, or I guess I should be, to be more accurate, then A prime is supported on a uniformly rectifiable set. Furthermore, the difference between the mass of T and the mass of T prime is at least some constant times the mass of this difference. So when we repeat the process, every time we do this, every time we take off another piece of T, the mass of T goes down. We get another piece in our decomposition, but the amount of decrease in the mass is bigger than a constant times the mass of the new piece in the decomposition. So the total mass of the pieces in the decomposition is bounded by the mass of T. And we have the decomposition we wanted. The sum of the A sub i's is equal to T, and the sum of the mass of the A sub i's is less than a constant times the mass of T. So we can decompose we can do a decomposition like this in higher codimension, again with the same caveats. We need to do this cubical approximation so that we have we need to do this cubical approximation so that we know that there is some smallest set with this property, and we need these mod 2 coefficients. As far as we know, this doesn't quite work for integer coefficients. So, is this okay so far? And so the application, the application here. So again, what do we want to do? We want to study arbitrary mod 2 cycles by breaking them up into uniformly rectifiable pieces, and then saying something about the uniformly rectifiable pieces. And so there are a few things we can do with this related to notions of orientability. So some of the things we can do with this, we can show that every Z mod 2 current lifts to an integer current. We can define the quantitative non-orientability. We can define, we can use this to measure how non-orientable some non-orientable surface is in a scale invariant way. And there's a weird, how much time do I have? There's a weird old question about filling areas, which is the following. Say I have a curve. I define the filling area of the curve to be the minimum area of a disk whose boundary is that curve. So for instance, if I have if I have a curve in the plane like this, then I can count it by a winding number. I have the filling area is this area plus this area plus this area plus 2 times this area. And you can ask, if I draw that curve twice, if I look for a chain that fills that curve with multiplicity 2, what happens to the filling area? In the plane, all these winding numbers double, so the filling area doubles. But in higher dimensions, there is a weird phenomenon that you can have the filling area of 2 times the curve may be less than, strictly less than, 2 times the filling area of the curve. And the example, let me just quickly draw you the example because it's a very nice example. This is due to L.C. Young, who, as far as I know, is unrelated to me. But the example goes like this: you draw a bunch of circles. You draw 2n plus 1 circles, and then you orient them in opposite directions. up, down, up, down, up, down, up, down. Because you have an odd number of circles, the left circle and the right circle have the same orientation. So I want to close this up into sort of Klein bottle. So I put this in R4, I take the two ends, I bring them close to each other and I give one of them a twist. So if I do that, then now I have this Klein bottle in R4 where I have this odd number of rings around the Klein bottle where the rings are going in opposite directions all around the Klein bottle. That's going to be my curve T. What's the filling area of T? Well, wherever I have, if I have two neighboring circles like this, the natural thing to do is fill that with a cylinder. So I take this pair, I fill it with a cylinder. I take this pair, I fill it with a cylinder. I take n pairs and I fill them all with cylinders. That leaves me one curve left over, and I fill that with a disk. So the area of the filling area of the original curve is n of these cylinders plus the area of a disk. And if n is very large, that's basically half of the area of the Klein bottle plus a disk. The filling area of twice the curve, well, that gives me twice as many cylinders I can draw. So now I can fill in this cylinder here with the orientation like this, and this cylinder here with orientation like this, and go all the way around. Previously, I had a problem because I had an odd number of rings, and so there would always be one left over. But if I double it, I have an even number of rings, and I can just go all the way around and connect every pair of adjacent rings with a cylinder, in which case this filling area is the area of a Klein bottle. And this filling area is the area of Klein bottle plus two disks. And so that's essentially L.C. Young's example. He asked the question: is filling area of 2T always does there exist a C such that the filling area of 2T is greater than or equal to C times the filling area of T? How bad can you make this example? And so one application of this is to answer this question of L.C. Young and show that the filling area of 2T is always within a constant of the filling area of T. Okay. Okay, I think I'm going to stop there.
Thank you, Robert. Are there any questions?
Thank you. About what you just said, you have an idea of the constant?
Oh, it's something very, very small. And like you can't even the question people always ask is, okay, can you show that the filling area of 2T is always bigger than the filling area of T? You can't even show that. But this is saying that the filling area of 2T is, at least 10 to the minus 1,000 times the filling area of T, because like the paper that does this decomposition, I've simplified it a lot. The paper that does this decomposition takes 40, 50 pages. And the theorem of David and Sem's that quasi-minimizing sets are uniformly rectifiable is a monograph. It takes 120 pages. So the constants get really bad.
Any other questions? Comments? If not, let's thank again Robert. And we would like to thank again all the speakers of this week. Thank you so much, everybody.